What if the universe, your body, and even your own mind are far stranger than they appear? We will journey through 30 remarkable questions, from hidden dimensions and newborn universes inside black holes to the secret signals inside your brain, the invisible colors seen by bees, and the ancient forces quietly reshaping your body every second. Along the way, we will separate fascinating science from exaggeration and discover what these mysteries truly reveal about reality. Before we begin, tell me in the comments where you are listening from and what time it is there. And don't forget to like the video and subscribe for more calm, mind-opening science. Now get comfortable, let the noise of the day fade away, and let us begin. Why the universe exists at all instead of nothing. The strangest fact in the universe is not that stars explode, that black holes bend time, or that galaxies drift through darkness. It is that anything exists at all. You are here inside a reality filled with matter, light, motion, memory, and thought. Yet no experiment has revealed why there is a universe instead of complete absence. This question sounds simple until you try to define what nothing actually means. An empty room is not nothing because it still contains air, space, radiation, and physical laws. The darkness between galaxies is not nothing either, because invisible fields still extend through it. Gravity still acts within it, and brief quantum fluctuations can occur there. Even a perfect vacuum in modern physics is not an absolute void. It is the lowest energy state of fields that already exist. True nothingness would mean no particles, no space, no time, no laws, no possibilities, and no background in which anything could begin. The difficulty is immediate. If there were truly nothing, there would be no mechanism capable of changing that condition. There would be no clock waiting for a first moment, no law allowing a universe to appear, and no probability that could eventually produce one. Nothing could not evolve, fluctuate, or become unstable, because all of those ideas already assume that something exists. This is why the question has survived every scientific revolution. Cosmology can describe how the universe changed from an extremely hot and dense early state, but the Big Bang theory does not by itself explain why reality exists. It tells us that the observable universe was once much hotter, smaller, and denser, and that space has been expanding for roughly 13.8 billion years. It does not necessarily describe an explosion into empty surroundings, and it does not prove that everything emerged from absolute nothingness. When physicists trace cosmic history backward, their equations eventually reach conditions where current theories become incomplete. At that boundary, familiar ideas such as space, time, cause, and before may no longer work in the ordinary way. Asking what happened before the beginning of time may be like asking what lies north of the North Pole. The grammar of the question feels correct, but the reality it assumes may not exist. Some models propose that the universe could arise through quantum processes, while others suggest that time has no sharp starting edge, and that the early universe was more like a smooth boundary than a first ticking second. These ideas are serious attempts to understand cosmic origins, but they remain proposals, not confirmed descriptions of creation from literal nothing. A quantum state still obeys rules, a vacuum still contains structure. A mathematical possibility still depends on a framework in which possibility has meaning. So even if physics eventually explains how universes can emerge naturally, a deeper question remains beneath the explanation. Why do those laws exist? And why is there a framework capable of producing anything? One possible answer is that existence may be a brute fact. Perhaps the universe has no further explanation, just as logic does not explain why logic is logical. This can feel unsatisfying because your mind is built to search for causes. Every event in ordinary life seems to come from something earlier. A flame comes from a spark, a tree comes from a seed, and a thought arises from activity in the brain. You naturally carry this pattern outward and expect the entire universe to have a cause as well. But causation is something observed within the universe. It is not obvious that the universe as a whole must obey the same kind of explanation as the objects inside it. A page in a book has a previous page, but the book itself does not need to be another page. In the same way, Every event in time may have an earlier condition without reality itself requiring an earlier moment outside time. Another possibility is that absolute nothingness was never genuinely possible. Perhaps existence is necessary in some form, while nothingness is only an idea the human mind creates by mentally removing objects one by one. You can picture an empty field, remove the field, remove space, remove time, and continue subtracting in thought. But you may never actually conceive nothing. The moment you picture darkness, emptiness, or silence, you have already pictured something. Even your idea of absence is held inside an existing mind. This does not prove that reality had to exist, but it reveals how difficult it is for a creature made from existence to understand its opposite. Other explanations suggest that there may be countless universes, each with different conditions, and that we naturally find ourselves in one where stars, chemistry, planets, and observers can develop. This may help explain why our universe appears suitable for complexity, but it does not fully answer why any collection of universes exists. Moving from one universe to many changes the size of the mystery without removing it. The same is true of a creator. Such an answer may provide meaning within a religious or philosophical worldview, but it raises a further question about why that creator or underlying reality exists. Every proposed foundation seems to rest on another foundation until thought reaches a point where explanation can go no deeper. And perhaps this limit tells you something important. The universe is not obligated to fit the structure of human intuition. Your brain evolved to navigate distances, recognize danger, find food, and understand other people. It was not shaped to comprehend the origin of all being. Yet this small biological mind can still turn toward the whole of existence and ask why it is here. That may be one of the most extraordinary things the universe has produced. Matter arranged into a form capable of questioning matter, a temporary collection of atoms becoming aware that there might have been no atoms at all. You may never receive a final answer. Science may push the boundary farther back, describing earlier states, deeper laws, and more fundamental structures, but the final why may remain beyond measurement. Still, the absence of an answer does not make the question empty. It changes the way you see ordinary things. A glass of water, the warmth of your hand, a distant star, and the quiet awareness behind your thoughts are no longer merely familiar objects. They are examples of the central mystery. Existence has happened. Against the concept of absolute absence, reality is here, unfolding in countless forms, and for a brief moment it has become conscious through you. Perhaps the deepest response is not a theory, but a quieter recognition. Before asking what purpose the universe has, you can pause and notice that there is a universe capable of containing purpose. Before searching for meaning beyond existence, you can recognize how strange it is that meaning can arise at all. The question remains open, resting beneath every law of physics and every moment of your life, but it does not have to feel like a void. It can feel like a doorway, one that may never fully open, yet continues to remind you that the most familiar fact of all, the fact that something is here, may also be the greatest mystery you will ever encounter. Every black hole may contain another universe. A black hole may be less like a cosmic grave and more like a sealed beginning, a region where collapsing matter does not simply end, but could open into an expanding world that no observer outside can ever enter or see. This possibility is not an established fact, and astronomers have found no evidence that real black holes contain universes. Yet it emerges from serious attempts to understand what happens after matter crosses an event horizon. From far away, a black hole appears remarkably simple. It can be described mainly by its mass, rotation, and electrical charge, while the material that formed it disappears behind a boundary from which light cannot return. But crossing that boundary would not be like striking a solid surface. For a sufficiently large black hole, you might pass the event horizon without noticing a sudden wall or flash. The danger lies deeper inside, where gravity forces every possible route toward a region that classical general relativity describes as a singularity. A singularity is not necessarily a physical object sitting at the center. It is a warning that the theory has reached conditions it cannot describe, producing infinite density and a breakdown of the familiar structure of space and time. Most physicists, therefore, do not treat the singularity as a complete picture of nature. They expect that a future theory combining gravity with quantum physics will replace it with something more meaningful. One possibility is a bounce. Instead of collapsing without limit, matter could reach an extreme but finite density, where unknown quantum effects resist further compression. The inward collapse might then reverse into expansion. From the viewpoint of that expanding region, the event could resemble the birth of a new cosmos, while observers in the parent universe would see only a black hole. Researchers have constructed theoretical models in which collapsing material transitions into an expanding, self-contained space-time, but these remain simplified models rather than confirmed descriptions of real black hole interiors. Archive. The phrase, "a universe inside a black hole," can be misleading because it encourages you to picture a tiny galaxy-filled sphere hidden inside a larger object, like a room concealed within a building. General relativity allows something much stranger. The geometry inside an event horizon does not have to match the black hole's apparent size from the outside. A horizon only a limited distance across can hide an interior space-time whose volume grows enormously. The new region would not need to sit inside our space in the ordinary sense. It could develop its own distances, direction of time, expanding geometry, and perhaps its own vast future. The connection to the parent universe might narrow and eventually become causally useless, meaning that no signal from the new cosmos could travel back through the horizon to announce what had formed. It would become what physicists often call a baby universe, a region initially related to another space-time, but later evolving as a largely independent cosmos. Archive. This would also explain why entering the black hole would not give you a practical route to another universe. In realistic black holes, tidal forces, radiation, instability, and the one-way nature of the horizon make survival doubtful, and the hypothetical new region would not function like a doorway that could be crossed in both directions. The familiar Einstein-Rosen bridge, often called a wormhole, appears in idealized solutions of Einstein's equations, but its simplest form closes too quickly to be traversed. The baby universe idea requires additional physics to prevent the interior from ending at a singularity and to allow a new expanding region to develop. That missing physics is precisely the part scientists do not yet possess. Still, the proposal attracts attention because it connects two events that seem opposite: gravitational collapse and cosmic expansion. A massive star exhausts its fuel, loses the pressure supporting it, and falls inward. If quantum gravity eventually turns that collapse into a bounce, then what looks like an ending from one side could look like a beginning from the other. The parent universe would lose access to the collapsing matter, while the child universe could inherit energy from it and expand into a future of its own. Some models even ask whether our observable universe might have formed behind the horizon of a black hole in a larger parent cosmos. Such scenarios can sometimes reproduce selected cosmological features, but they have not produced decisive evidence that distinguishes them from more conventional explanations. A compelling mathematical possibility is not the same as an observation. No telescope can look through an event horizon, and anything happening behind it is hidden by definition. Scientists must therefore search for indirect consequences, subtle patterns in cosmic expansion, spatial curvature, black hole evaporation, or the behavior of quantum information. But no accepted measurement currently shows that our universe was born inside a black hole. Recent theoretical work continues to explore cosmological spacetimes associated with black hole interiors, including simplified holographic models, showing that the subject remains active while still deeply speculative. Archive. The idea also faces difficult questions. If a baby universe separates from its parent, what happens to the information carried by everything that fell into the black hole? Does that information remain encoded at the horizon, enter the new universe, or appear in the faint Hawking radiation released as the black hole slowly evaporates? Can one physical history be described consistently from both the exterior and interior? Would every black hole create a universe, or only black holes with particular masses, rotations, or internal conditions? And if new universes form, would they inherit the same physical laws as their parent? Or would small variations appear during the bounce? None of these questions has a settled answer. There are also theoretical arguments that restrict which kinds of causally disconnected baby universes can form, while other models suggest that the interior may pinch off only under special conditions. The science is therefore not a single confident claim, but a landscape of competing possibilities. Arcevo. Yet the proposal changes how you can think about a black hole without requiring you to believe it. What appears externally as darkness may conceal not an empty cavity but an evolving geometry. What looks like matter being erased may instead be matter entering a region whose future points somewhere inaccessible to us. A black hole would then be defined not only by what it removes from our view, but by what it might allow beyond that view. Each collapsing star could become a one-way boundary between two cosmic histories. One universe watching a black horizon form, another beginning its expansion without ever seeing the sky from which it came. If this process occurred repeatedly, universes might produce stars, some stars might produce black holes, and some black holes might produce further universes. Reality would resemble a branching cosmic ancestry, rather than a collection of parallel worlds floating beside one another. But honesty requires leaving the final image unresolved. We do not know what replaces the singularity. We do not know whether space-time continues into a new expanding region. We do not know whether even one black hole has created a universe. What we know is that our current theories become incomplete exactly where the possibility begins, and that mathematically consistent models allow physicists to investigate it without presenting it as fact. The event horizon therefore marks more than the boundary of escape. It marks the boundary of tested knowledge. Beyond it, matter may be crushed toward an unknown quantum state, transformed into information we do not yet understand, or carried into a new cosmic expansion hidden forever from its parent world. You may never be able to look inside and learn which answer is correct, but that limitation is part of what makes black holes so scientifically powerful. They force physics to confront the point where its clearest laws stop speaking, and they leave you with a restrained but extraordinary possibility, somewhere behind a surface of perfect darkness. Collapse may not be finishing a story at all. It may be beginning one that can never send a message home. The past, present, and future may all exist simultaneously. The moment you call now may not be moving through the universe at all. It may be only the narrow point from which your mind is reading a much larger structure. In everyday life, time feels like a river. The past has disappeared, the future has not yet arrived, and the present keeps carrying you forward. Physics, however, does not clearly support the idea of one universal present shared by everything. Einstein's theory of relativity revealed that observers moving differently can disagree about whether distant events are happening at the same time. Two flashes that appear simultaneous to one observer may occur at different moments for another, and neither observer is simply mistaken. Their measurements depend on how they are moving through space. This is called the relativity of simultaneity, and it quietly removes one of the deepest assumptions built into human experience: the idea that the entire cosmos advances together beneath a single invisible clock. There may be no universal now stretching across the universe. Your present moment belongs to your position and motion, not necessarily to a cosmic present shared by a distant planet or another observer passing you at great speed. This has inspired a view known as the block universe, or eternalism. In this interpretation, reality is a four-dimensional structure containing locations in time, as well as locations in space. Your birth, this moment, and the final day of your life would all occupy different regions within that structure, much as different cities occupy different places on a map. London does not cease to exist because you are currently in Istanbul. In the same way, the past might not vanish merely because you are no longer experiencing it, and the future might not be unreal merely because you have not reached it. You encounter events one after another, but the full pattern may exist as a complete space-time history. This does not mean that you can visit yesterday as easily as another room, nor does it prove that every future detail is fixed in the way fate is often imagined. The block universe picture is a philosophical interpretation of physical theories, not a directly photographed object. Relativity describes relationships between events with extraordinary accuracy, but physicists and philosophers still debate what those relationships tell us about the true nature of time. Some believe all moments are equally real. Others argue that only the present exists, even though defining that present across great distances becomes difficult. Another view suggests that the past and present exist while the future gradually comes into being. Science has not chosen one of these interpretations as the final answer. Yet, relativity gives the simultaneous existence idea real weight, because what one observer calls the future can overlap with what another considers the present, depending on their motion and distance. There is no contradiction because information still cannot be transmitted in a way that breaks cause and effect. You cannot receive tomorrow's memories or warn your earlier self. The order of events that can influence one another remains protected. But for distant events with no time for a signal to pass between them, the universe does not always provide an absolute answer about which occurred first. Their order can depend on the observer. This suggests that the division between past, present, and future may not be carved into reality as sharply as it is carved into consciousness. Your brain creates a special feeling of the present by gathering sensory information, comparing it with memory, and assembling it into a brief window of experience. That window feels immediate, yet it already contains tiny delays. Light must reach your eyes, sound must reach your ears, and neural signals must be processed before a moment becomes part of awareness. You never experience the world at a perfectly dimensionless instant. You experience a short construction that your mind labels now. Memory gives the past its emotional solidity, while uncertainty makes the future feel open. The difference may therefore arise partly from how you access time, rather than from how time exists outside you. You possess records of earlier events, but none from later ones. So one direction feels finished and the other feels unwritten. Entropy, the tendency for usable energy to spread and ordered systems to become more disordered, helps create this direction. You remember an intact glass before it shattered, because physical traces of the earlier state remain, while no ordinary process provides memories of the scattered pieces assembling themselves in advance. This arrow of time explains why life feels directional, even if the underlying space-time structure does not literally flow. A film reel offers a useful but imperfect comparison. Every frame can already be present on the reel, while the projector reveals them in sequence. The characters within one frame cannot see the whole strip, and the existence of later frames does not allow them to skip ahead. Your awareness may behave somewhat like that projector, illuminating one limited region of a larger temporal structure. But the analogy has limits because there is no known external machine moving consciousness from frame to frame, and physics has not identified a separate substance called the flow of time. Equations describe change, duration, and relationships between events. They do not clearly contain the sensation of time passing. That sensation may be something your nervous system adds as it organizes change into a continuous life. This possibility can feel unsettling because it seems to place your future somewhere ahead, as though it were already complete. Yet even within a block universe, your choices remain part of the structure rather than meaningless decorations upon it. A decision is still produced by your reasoning, character, circumstances, and attention. The fact that an event has a place in space-time does not mean it happens without you. Your deliberation is one of the causes shaping what follows. A mountain's presence on a map does not mean the path toward it requires no walking. In the same way, a future event could exist as part of space-time, while still depending on the choices through which it occurs. The deeper challenge is not whether you are free in some absolute sense, but whether a complete history can include genuine acts of thinking and deciding. Many philosophers believe it can, others disagree, and the debate remains open because physics alone may not settle what human freedom means. What the theory changes most powerfully is your relationship with disappearance. If the past remains part of space-time, then lost moments may not have been erased from reality. A childhood afternoon, a forgotten conversation, or the final breath of someone you loved could still occupy its own location in the history of the universe, even though you cannot return to it. From your perspective, it is gone. From the perspective of the block, it may simply be elsewhere in time. This is not evidence of an afterlife, nor does it allow communication with the past. It offers something quieter, the possibility that events do not fall into non-existence when the present moves beyond them. They remain woven into the structure that made every later moment possible. Perhaps the future is there as well, not watching you, not pulling you forward, but existing as the continuation of a pattern you can only encounter piece by piece. You still wake, choose, lose, learn, and grow in sequence, because sequence is how a human life is experienced. Yet beneath that intimate passage, reality may hold every moment without favoring the one you happen to occupy. The present feels like the center because awareness is standing inside it, just as every place feels nearby when you are the one standing there. And when this moment passes, it may not be destroyed. It may simply become another permanent coordinate in the vast architecture of space-time, a quiet part of the universe that can no longer be reached, but may never truly cease to exist. Your decisions may be made before you are aware of them. Your hand may begin preparing to move before the voice in your head has decided that it will. And that small delay has forced scientists to question whether conscious choice begins where it feels as though it begins. You experience a decision as a clear internal event. First you choose, then your body obeys. Yet the brain does not wait in silence for consciousness to issue a command. Long before an action reaches awareness, networks involved in memory, emotion, attention, reward, and movement are already evaluating possibilities. They compare what is happening now with what happened before, estimate possible outcomes, and quietly push some actions closer to execution while holding others back. By the time a choice becomes a sentence in your mind, "I will do this," much of the work behind it may already be underway. One of the most famous attempts to measure this hidden preparation was performed by neuroscientist Benjamin Libet and his colleagues. Participants watched a rapidly moving clock, chose for themselves when to flex a wrist or finger, and later reported the moment they first became aware of the intention to move. Electrical recordings revealed a gradual change in brain activity, known as the readiness potential, beginning several hundred milliseconds before the participants reported consciously wanting to act. The result appeared to suggest that the brain had started preparing the movement before the person felt that the decision had been made. This finding became famous because it seemed to place conscious awareness behind the action rather than in command of it. If the brain begins first and consciousness learns about the choice later, then perhaps the feeling of deciding is only a report delivered after an unconscious system has already selected the outcome. But the experiment did not prove that free will is an illusion, and it did not show that the entire decision had been completed before awareness. It measured simple, purposeless movements in which participants had no important reason to choose one moment rather than another. Deciding when to twitch a finger is very different from deciding whether to leave a career, forgive someone, tell the truth, or change the direction of your life. In such meaningful choices, you weigh memories, values, consequences, and competing goals, sometimes for minutes, months, or years. The conscious reflection occurring during that period is itself brain activity. It is not a ghost standing outside the nervous system. Later experiments made the mystery more dramatic. In one study, researchers used brain scans while participants freely chose whether to press a button with the left or right hand. Patterns in frontal and parietal regions carried information about the eventual choice as much as several seconds before participants reported becoming aware of it. Yet the researchers could not predict every decision with certainty. The patterns offered a statistical advantage over guessing, not a perfect preview of an unavoidable future. This distinction matters. A weak early signal may represent a developing preference, a temporary bias, or one option becoming slightly more likely, not a finished command carved permanently into the brain. Your decision may begin unconsciously without being completed unconsciously. Think of several quiet streams feeding a river. One carries habit, another emotion, another recent experience, and another the goal you are deliberately trying to follow. Conscious awareness may not create every stream, but it can become part of the current, redirecting attention, imagining consequences, and strengthening one route over another. The moment you notice the decision may therefore be neither its absolute beginning nor a meaningless afterthought. It may be one stage in a process distributed across time and many brain systems. Scientists have also challenged the traditional interpretation of the readiness potential itself. Rather than representing a hidden brain command that has already decided to move, it may partly emerge from random fluctuations in neural activity. When people are told to move whenever they feel like it, without a reason or external signal, these fluctuations can gradually approach a threshold that triggers action. If researchers align many recordings to the moment of movement and average them together, the result can look like a smooth build-up, even though no single unconscious decision began at one precise earlier instant. This accumulator explanation suggests that the readiness potential may reveal how spontaneous actions emerge from ongoing neural noise, rather than the moment the brain secretly makes a final choice. The difference becomes clearer when arbitrary choices are compared with meaningful ones. In a study involving real charitable donations, researchers asked participants either to make inconsequential button choices or to decide which non-profit organization should receive money. The familiar readiness potential appeared clearly before arbitrary actions, but was absent or greatly reduced before the deliberate decisions that depended on personal values. The researchers warned that conclusions drawn from meaningless laboratory movements cannot safely be extended to serious choices. This does not mean important decisions appear from nowhere or escape physical causes. Every choice you make depends on a living brain shaped by genes, upbringing, culture, bodily condition, memory, and the immediate environment. Hunger can change patience. Fear can narrow attention. A familiar voice can influence trust before you identify why. Damage to particular brain regions can alter judgment, impulse control, and personality. The conscious self is therefore not an independent ruler sitting above biology. It is an activity produced through biology. But saying that your brain influences your decision is not the same as saying that something other than you made it. Your brain is not a stranger operating behind your back. Its unconscious processes contain your learned skills, emotional associations, values, and experiences, including memories you cannot deliberately summon at every moment. When an experienced driver brakes before consciously identifying danger, the reaction is not evidence that the driver has disappeared. It is evidence that learning has become fast enough to work beneath awareness. Conscious thought is slow and limited, so the brain automates much of life. You do not consciously calculate the position of every muscle when standing, select each word through a complete search of your vocabulary, or examine every possible interpretation of a face. If awareness had to manage every detail, even a simple morning would become impossible. The deeper question, then, is not whether unconscious activity comes before conscious awareness. It often does. But what consciousness contributes once it enters the process. Awareness can hold a goal in mind, interrupt a habit, reconsider an impulse, seek new evidence, and create rules that influence future automatic behavior. You may feel anger before choosing it, but you can decide whether to speak through it. You may experience an urge to reach for something, yet pause when you remember a larger purpose. You can arrange your environment to make a future choice easier, practice a response until it becomes instinctive, or examine a prejudice that once guided you invisibly. Through repetition, conscious effort can reshape the unconscious machinery that later acts before awareness. The part of you that reflects today can train the part of you that reacts tomorrow. This means freedom may not consist of creating decisions from an empty place untouched by causes. Such a choice would not express your character at all. It would be random. A more realistic form of freedom may be the brain's ability to consider reasons, learn from mistakes, resist certain impulses, and gradually change the forces that shape its own behavior. Your conscious experience may not be the first spark of every decision, but it can still be part of the fire's direction. Neuroscience has shown that the feeling of choice is less simple than it appears. Not that human agency has been scientifically erased. Beneath each decision lies a hidden preparation you cannot fully observe. Yet within that preparation are the habits you practiced, the lessons you accepted, the values you protected, and the attention you chose to cultivate. The decision may begin before you hear it in words, but the mind that prepared it has been forming across your entire life. Perhaps consciousness is not a commander who arrives before every action. Perhaps it is something more patient, a participant that watches, corrects, rehearses, and slowly teaches the unseen brain what kind of person it should be ready to become. The universe may have more than 3 dimensions. The room around you may contain directions that your body can never enter, hidden not behind a wall or beyond a distant galaxy, but folded so tightly into every point of space that you pass through them without ever knowing they are there. Human experience is built around 3 spatial dimensions. You can move left and right, forward and backward, upward and downward. Every object you touch has some combination of length, width, and height, and your brain has evolved to navigate this 3-dimensional environment so naturally that any additional direction seems almost impossible to picture. Yet mathematics does not stop at 3 dimensions, and some of the most ambitious theories in physics suggest that nature may not stop there either. An extra dimension would not simply be another place hidden somewhere far away. It would be a new independent direction, one that cannot be reached by moving through any combination of the directions you already know. A creature living on a perfectly flat surface would understand forward, backward, left, and right. But the idea of moving above that surface would lie outside its entire experience. You could lift an object from its world, move it through the 3rd dimension, and return it somewhere else without crossing any path the creature could observe. To the flat creature, the object might appear to vanish and reappear. A 3-dimensional object passing through its world would be seen only in changing slices. A sphere would first appear as a point, grow into a circle, then shrink and disappear. In the same way, if a higher dimensional object passed through our space, you might perceive only a sequence of changing 3-dimensional sections, rather than the complete object itself. This does not mean unexplained disappearances or strange visions are evidence of higher dimensions. It simply shows why a mind confined to 3 dimensions would struggle to recognize a larger geometry. The serious scientific interest in extra dimensions began partly from an attempt to unite forces that appear separate. In the early 20th century, physicists explored whether adding a small additional dimension could allow gravity and electromagnetism to be described within one geometric framework. The idea was elegant but incomplete, and it did not accurately explain all the particles and forces later discovered. Still, it introduced a powerful possibility. What appears to be a force in 3 dimensions might be the visible effect of geometry in a higher dimensional space. Decades later, versions of string theory revived this possibility on a far greater scale. In these theories, the most fundamental ingredients of nature are not point-like particles, but extremely tiny vibrating structures. Different patterns of vibration could appear to us as different particles, much as different vibrations of one string can produce different notes. But the mathematical consistency of the theory typically requires more dimensions than the 3 you experience. Common versions use 10 dimensions of spacetime, while a broader framework known as M-theory uses 11. This does not mean scientists have discovered 7 hidden directions. It means the equations appear to work properly only when those extra dimensions are included. The challenge is explaining why they are invisible. One proposal is that the additional dimensions are compactified. curled into shapes so small that ordinary objects cannot move through them in any noticeable way. A garden hose seen from a great distance looks like a one-dimensional line extending along the ground, but an insect close to it could also travel around its circular surface. The curved direction was always present. It was simply too small to notice from far away. Extra dimensions might exist in a similar way at scales vastly smaller than an atom. At every point in the space you know, there could be a tiny folded geometry containing directions inaccessible to your senses and present-day instruments. These hidden shapes would not be meaningless decoration. Their geometry could influence how fundamental structures vibrate, helping determine which particles exist, how massive they are, and how strongly they interact. In this picture, some properties of matter that appear arbitrary might be shadows of a deeper spatial architecture. The universe would not merely contain particles moving through an empty stage. The hidden shape of the stage itself could help decide what kinds of actors are possible. This is one reason extra dimensions remain intellectually attractive. They offer a potential explanation for why nature has the particular collection of particles and forces we observe. But attractiveness is not proof. String theory has produced important mathematical insights, yet it has not provided experimentally confirmed evidence that these additional dimensions physically exist. There are also many possible ways the hidden dimensions could be folded, and different shapes can lead to different low-energy universes. Scientists have not yet shown why nature would select the specific geometry that produces the world around you. Another family of ideas proposes that the extra dimensions might not all be tiny. Our visible universe could be a three-dimensional surface, often called a brane, embedded in a larger, higher-dimensional region known as the bulk. Ordinary matter and light might be confined to this surface, while gravity could extend into the surrounding dimensions. This has been explored as one possible explanation for why gravity appears extraordinarily weak compared with the other fundamental forces. A small magnet can lift a metal object against the gravitational pull of the entire Earth. Perhaps gravity is not intrinsically so weak. Perhaps part of its influence spreads into directions that matter and light cannot follow. This remains speculative, but it creates testable consequences. If gravity enters extra dimensions at very short distances, its behavior might deviate slightly from the familiar pattern measured at larger scales. Researchers have therefore performed delicate experiments to test gravity across tiny distances, searching for unexpected changes. Particle colliders have also looked for signs that collisions might send energy into hidden dimensions or produce heavy partner states associated with movement through them. So far, no confirmed signal has appeared. The absence of evidence does not prove extra dimensions are impossible, but it places limits on how large they can be and how strongly they can affect known physics. Some proposed versions have already been restricted or ruled out by experiments, while others remain far beyond current technology. This is how the idea must be understood, not as a revealed secret of the cosmos, but as a carefully studied possibility living at the frontier between mathematical consistency and physical evidence. Higher dimensions also force you to reconsider what it means to see the whole of something. Your senses do not reveal reality in its entirety. They reveal the features that were useful for surviving at human scales. You cannot directly perceive radio waves, magnetic fields, or the microscopic movement of molecules, yet instruments confirm that they are present. It is therefore not unreasonable to ask whether spatial structure also extends beyond direct perception. But there is an important difference between something being difficult to sense and something remaining unconfirmed. Radio waves can be generated, detected, and measured repeatedly. Extra spatial dimensions have not yet reached that status. They remain explanations searching for decisive evidence. If they do exist, their effects may be hidden because the dimensions are extremely small, because ordinary particles are trapped within three-dimensional space, or because the energies required to probe them are far beyond anything humans can produce. It is also possible that nature truly has only three large spatial dimensions, and that theories requiring more are useful mathematical frameworks rather than literal descriptions of reality. Physicists must distinguish between a model that is beautiful, a model that calculates successfully, and a model that accurately describes the universe. Sometimes all three coincide, sometimes they do not. The mystery deepens when you ask why exactly 3 spatial dimensions became large enough for complex structures to form. In spaces with very different numbers of large dimensions, stable planetary paths, long-lived atoms, or familiar forms of causality might behave differently or fail to exist. Some researchers have explored whether 3 dimensions are especially suitable for stable complexity, though such arguments depend heavily on assumptions and do not provide a final explanation. Perhaps the universe began with more dimensions, and only 3 expanded while the others remained compact. Perhaps hidden geometry was fixed by conditions in the very early cosmos, or perhaps the number 3 reflects a deeper principle no current theory has uncovered. Each possibility reminds you that even the most ordinary fact, that you can move in 3 independent directions, may contain an unanswered scientific question. You live so completely inside this geometry that it feels inevitable, yet it may be only one visible layer of a larger structure. A higher dimensional universe would not necessarily look magical from within. Its hidden directions might quietly determine particle properties, influence gravity, and shape physical law without ever producing a doorway you could step through. There may be no dramatic edge where ordinary space ends and another dimension begins. The additional directions could be woven into the same space occupied by your body, present at every point, but inaccessible in the way the thickness of a page is inaccessible to a drawing printed upon it. Your brain is running on electrical signals, not reality. The reality you experience may depend less on how much electrical activity fills your brain than on whether distant regions manage to fire together at the right moment. Your visual system separates a single scene into many hidden tasks. Some cells respond to edges, others to color, depth, movement, or faces, while different networks process sound, touch, memory, and emotion. No single place inside the brain receives a complete copy of the world. Instead, awareness appears to emerge when these scattered electrical patterns become coordinated, allowing separate details to be experienced as one event. This creates what neuroscientists call the binding problem. If color is processed in one region and motion in another, how do you see one red car moving rather than redness, shape and movement as unrelated fragments? One leading idea is that timing helps unite them. Groups of neurons produce repeating rhythms, and networks that temporarily synchronize may exchange information more effectively, like musicians following the same beat. Attention can strengthen this coordination, making one object clearer while competing details fade. Your experience of reality may therefore be assembled through brief windows in which selected signals are linked, compared, and given priority. This also helps explain why consciousness can disappear even when the brain remains electrically active. Under general anesthesia, neurons do not simply switch off. Many continue firing, and sensory signals may still enter parts of the brain. Yet communication between distant regions becomes disrupted or less flexible. Information can remain trapped in local circuits instead of spreading through the larger networks associated with conscious experience. The brain is active, but the coordinated conversation that normally creates an integrated world has weakened. Sleep reveals another version of this change. The electrical rhythms of the brain shift. Connections between regions are reorganized, and awareness of the environment becomes reduced, even though the nervous system continues working. Conscious reality is therefore not produced by electricity alone. A storm contains electricity, and a computer carries currents, but neither automatically creates the experience of a room, a memory, or a self. What matters is the organized pattern, the structure of communication, and the brain's ability to combine information across many systems. Timing is especially important because the senses do not deliver their messages at identical speeds. Light and sound from the same event reach the body differently, and neural pathways require different amounts of processing. The brain quietly adjusts these delays so that a person's moving lips and voice usually seem connected. When the mismatch becomes too large, the illusion breaks and the sound appears detached from the image. This shows that the present you experience is not received whole from the outside world. It is constructed by aligning signals that arrived at different moments and treating them as belonging together. The process happens so smoothly that you rarely notice it, but your sense of a unified now depends on constant electrical negotiation. Even attention is not a spotlight controlled by a separate observer inside your head. It is a change in the way neural networks compete and cooperate. Signals related to your goals become stronger, more synchronized, or more influential, while other activity is suppressed. This is why you can fail to notice an obvious object while concentrating intensely on something else. The information may reach the eyes and activate parts of the visual system, yet it never becomes dominant enough to enter the organized pattern of awareness. Reality does not vanish, but your experienced version excludes it. That distinction is essential. The external world continues independently of your attention, but the world available to consciousness is always selective. Your brain must choose because it has limited capacity and unlimited incoming information. It cannot present everything with equal clarity, so it builds a useful scene from what seems most relevant at that moment. This means the electrical reality inside your skull is not a faithful miniature of everything outside it. It is a changing coalition of signals, continually updated as attention shifts, memories activate, and new evidence arrives. A face can suddenly seem familiar when the correct network joins the pattern. A confusing sentence can become obvious when context reorganizes its meaning. A threat can dominate awareness so strongly that neutral details disappear. In each case, the sensory input may change very little while the coordination of the brain changes dramatically. You do not merely receive a world. Your nervous system decides which parts will be joined into the world you consciously inhabit. Yet this should not lead you to believe that truth is entirely personal. Electrical patterns are constrained by what actually happens. Reliable perception survives because the brain repeatedly tests its internal activity against consequences. If its timing, expectations, or interpretations are wrong, movement fails, predictions collapse, and the model must be corrected. What neuroscience reveals is not that reality is unreal, but that conscious access to it is an achievement rather than a direct view. Billions of cells must coordinate across fractions of a second to give you one stable room, one continuous voice, one body, and one present moment. The world feels seamless because the brain hides the seams. Beneath that calm surface, signals compete, rhythms align, networks separate and reconnect, and only a small portion of the activity becomes the experience you call your life. You are not consciously watching the electricity that creates this experience. You are living inside the unity it produces. And perhaps that is the most unsettling and beautiful part. What feels like an immediate encounter with reality may actually be the final result of countless silent signals learning, for one brief moment, how to speak as one. A single photon can travel through every path at once. A photon can arrive at a detector as though it has explored routes no ordinary traveler could take, including paths that bend away from the destination, circle through space, and return. Yet when it is finally detected, it appears at only one place. This is the strange idea behind Richard Feynman's path-integral description of quantum mechanics, often summarized by saying that a particle travels through every possible path at once. The statement is powerful, but it must be understood carefully. A photon is not known to behave like a tiny glowing bead that consciously chooses thousands of roads and physically divides into countless visible copies. Instead, quantum theory assigns a probability contribution to every possible history, connecting the photon source to its destination. These contributions combine, strengthen one another in some places, and cancel one another in others. What eventually appears on a detector is determined by the total pattern created by all those possibilities. The clearest demonstration comes from single photon interference. Send photons one at a time toward an apparatus offering two possible routes, and each photon is detected as a single localized event. At first, the impacts seem scattered and random, but after many photons have arrived, the individual dots gradually form an interference pattern, the kind of pattern normally produced when waves overlap. This happens even when the photons are released so slowly that only one is passing through the apparatus at a time. Each photon therefore behaves as though both available routes contribute to its final outcome. If you block one route, the pattern changes. If you arrange the two routes so their quantum contributions reinforce one another at a certain detector, photons arrive there frequently. Adjust the distance slightly, and the same contributions can cancel, causing photons to avoid that detector almost completely. Nothing visible is pushing them away. The result comes from the way possible paths combine before measurement produces a definite event. This reveals a crucial difference between classical probability and quantum probability. When an ordinary object could have taken one of two roads, you may simply be ignorant of which road it used. Quantum interference suggests something deeper. Before the path is measured, the alternatives cannot always be treated as separate hidden routes, with one secretly chosen in advance. They remain part of one combined quantum process. Attempts to discover exactly which route the photon took usually destroy the interference pattern, because obtaining path information requires the photon to interact with a detector or environment. That interaction changes the physical situation and separates alternatives that were previously able to interfere. It is not human attention or eyesight that causes this change. A recording device can produce the same effect even if nobody checks its results until later. What matters is whether information about the path becomes physically available. Feynman extended this reasoning beyond two simple routes. In his formulation, nature considers every conceivable path between the starting and ending points. Some are nearly straight, some wander, some turn sharply, and some seem absurd from the perspective of everyday motion. Each path contributes with a kind of internal timing, and neighboring paths can either cooperate or oppose one another. For large objects, most wildly different paths cancel out. The contributions that remain strongest are clustered around the route predicted by classical physics, which is why thrown stones, moving cars, and orbiting planets appear to follow smooth, definite trajectories. Classical motion is not separate from quantum mechanics. It emerges when countless alternative histories cancel so efficiently that one narrow family of paths dominates. At microscopic scales, however, the cancellation is less complete, allowing several very different routes to influence the result. This is why quantum behavior seems so unfamiliar. Human intuition was shaped by large objects whose alternative paths have already faded into near invisibility. The phrase, "the photon takes every path," is therefore partly an interpretation of the mathematics, rather than a direct photograph of what the photon is doing between emission and detection. Quantum theory predicts experimental outcomes with extraordinary precision, but physicists continue to debate what its mathematical structure tells us about underlying reality. Some interpretations treat the many paths as genuine components of a quantum state. Others view them primarily as a calculation method for determining probabilities. What experiments establish is that all available routes can affect the final statistics, even when the photon is detected only once and cannot be caught occupying several ordinary locations like a classical object. This effect is not merely philosophical. It influences technologies that depend on quantum interference, including highly sensitive measurements, advanced imaging methods, and emerging forms of quantum communication and computation. Interferometers can detect changes far smaller than ordinary instruments could reveal, because even a tiny alteration in one possible route changes how the quantum contributions recombine. The photon becomes a probe of differences that would otherwise remain hidden. It does not need to leave a continuous trail along each route. The final interference pattern carries information about the entire arrangement, yet there is a boundary to what can be known. If you insist on assigning one perfectly definite classical path to the photon, while also preserving the full interference pattern, quantum mechanics refuses to provide both descriptions at once. You can design an experiment that reveals path information, or one that reveals interference between paths, but the physical conditions required for one undermine the other. This does not mean the photon is playing tricks. It means the categories inherited from everyday objects, one route, one location, one continuous journey, may not apply before measurement in the way you expect. The photon's journey is represented not by a hidden line waiting to be discovered, but by a spread of possibilities whose relationships determine where a single event can occur. Once detection happens, the rich collection of alternatives leaves behind one small mark: a flash in a sensor, a chemical change, or an electrical pulse. You see the destination, but not a classical travel diary explaining how it arrived. And perhaps that is the deeper lesson contained in the photon's impossible journey. Nature may not always move from possibility to result by selecting one secret route at the beginning. At its smallest scales, the unrealized alternatives can remain active, combining and cancelling until an interaction forces the world to produce a record. The paths that never become visible are not meaningless. Without them, the visible outcome would be different. A single photon can therefore teach you something unsettling and precise. Reality may be shaped not only by what finally happens, but also by possibilities that leave no direct trace except through the pattern they create together. The vacuum of space is not empty. It boils with energy. Even the darkest, coldest region of space is not truly still, because removing every particle does not remove the invisible fields from which particles can arise. In everyday language, a vacuum means emptiness, but in modern physics, it means the lowest energy state available to the fields that fill space. Electrons are excitations of an electron field, photons are excitations of the electromagnetic field, and other particles are linked to other quantum fields. When no detectable particles are present, those fields do not disappear. They remain, and quantum theory says they cannot become perfectly motionless. Their values fluctuate slightly, leaving behind what is often called zero-point energy. This is why physicists sometimes describe empty space as boiling, although the phrase is only a metaphor. Space is not literally filled with tiny particles constantly popping into view like bubbles in water. Popular explanations often speak of virtual particles appearing and vanishing. But virtual particles are mainly elements used in calculations, not ordinary particles that can be directly photographed during brief secret lives. What experiments reveal are measurable effects showing that the vacuum has physical structure. One of the clearest examples is the Casimir effect. Place two uncharged conducting plates extremely close together, and the quantum fields between them are restricted differently from the fields outside. Only certain patterns fit within the narrow gap, while a broader range exists beyond it. This difference produces a tiny force that pushes the plates together. Nothing visible stands between them, yet the arrangement of the vacuum changes the outcome. Another sign appears inside atoms. An electron does not move through a perfectly silent background. It interacts with the quantum electromagnetic field even in its lowest state. This slightly shifts the energy levels of the atom, producing the Lamb shift, an effect measured with remarkable precision. The vacuum can also alter how quickly an excited atom releases light. Put the atom inside a carefully designed cavity, and the surrounding field patterns change, making emission faster or slower. Empty space is therefore not merely a passive container in which matter behaves. Its quantum structure helps influence what matter can do. Yet this does not mean the vacuum contains an unlimited supply of usable energy waiting to be extracted. Zero-point energy is the minimum state of the system, and there is no known machine that can continuously take energy from it without supplying energy or changing something else. The Casimir effect, for example, can release energy as plates move together, but separating them again requires at least as much work. Nature does not offer a free reservoir simply because the vacuum is not empty. The deeper puzzle appears when physicists ask how vacuum energy should affect gravity. In general relativity, energy influences the shape and expansion of space, so the energy of quantum fields should matter cosmologically. But straightforward theoretical estimates are enormously larger than the small effect associated with the observed acceleration of cosmic expansion. This mismatch is known as the cosmological constant problem, and it is one of the largest unresolved disagreements between quantum theory and gravity. The equations that work extraordinarily well for particles predict a vacuum contribution that does not fit the universe we observe. Scientists know that something important is missing, whether in the way vacuum energy is calculated, the way gravity responds to it, or the deeper framework connecting the two. The vacuum also depends on context. What one observer describes as empty may not appear empty to another observer moving differently or accelerating. According to the Unruh effect, an accelerating observer would describe the vacuum as containing a faint thermal background, even while an observer moving steadily calls the same region empty. This effect has not been directly measured in its pure form because the required acceleration is extreme, but it follows from well-established quantum field theory and reveals that nothing is not always an observer-independent condition. Near a black hole, related physics leads to Hawking radiation. The horizon changes how quantum fields are divided into particles and vacuum states for different observers. The radiation is not best understood as pairs of ordinary particles simply appearing at the horizon, despite the popular picture. It arises from how quantum fields behave in curved space-time and from the disagreement between different observers about what counts as a particle. This shows that a particle is not always a permanent little object hiding inside a field. It can be a way that an observer interprets patterns in that field. The vacuum is the foundation beneath those interpretations, not an absolute absence beneath existence. Even so, scientists must be careful not to turn quantum vacuum fluctuations into explanations for every mystery. They do not prove that entire universes casually emerge from literal nothing. They do not justify claims of limitless energy, and they do not mean that large objects can spontaneously appear in your room. Quantum fluctuations are tightly governed by physical laws, and their measurable effects usually become important only at very small scales or under extreme conditions. The uncertainty of a quantum field is not permission for anything imaginable to happen. It is a precise feature of a theory that predicts probabilities and experimental results with extraordinary accuracy. What makes the vacuum remarkable is not that it behaves like magic, but that emptiness itself has rules. If you removed every atom from a chamber, blocked ordinary light, lowered the temperature, and isolated the region as carefully as technology allowed, you would not reach philosophical nothingness. You would reach a physical state still containing fields, possible excitations, and a minimum level of quantum activity. The chamber would look empty because human senses do not detect the underlying structure directly, but sensitive experiments could still reveal its influence. This changes the meaning of space. It is not simply a blank distance separating objects, like untouched paper between written words. It is an active physical medium, although not a material substance like air or water, and its properties help define how particles exist and interact. Matter is not placed on top of nothing. Matter appears as organized activity within fields that are already present. The silence between stars is therefore not the absence of physics. It is physics in its quietest known state. You may look into darkness and see no objects, no motion, and no light. Yet beneath that apparent calm lies a structure that can shift atomic energies. Push metal plates, influence radiation, and challenge the way gravity is understood. The vacuum does not roar, glow, or reveal itself easily. Its effects are subtle because it is the baseline from which everything else is measured. But once you understand that even the lowest possible state is not perfectly blank, emptiness becomes less like a void and more like a restrained potential, a foundation that never becomes completely silent, even when the universe seems to contain nothing at all. Time may not have existed before the Big Bang. A clock cannot tick before time exists, and this is why the phrase "before the Big Bang" may be asking for a moment that nature never contained. Time feels like an invisible stage on which the universe performs, but modern physics treats it as part of the performance itself. In general relativity, space and time form a connected structure whose geometry changes with matter and energy. Clocks do not measure a universal river flowing independently in the background. They measure duration along particular paths through space-time. If the earliest boundary of the universe is also the boundary of space-time, then there may have been no earlier arena, no waiting darkness, and no empty sequence of moments counting down toward creation. the Big Bang would not have occurred at one location inside an older universe. It would mark the limit from which the expanding history described by our classical equations can be traced. This statement must be handled carefully, because the phrase Big Bang is used in two different ways. It can refer to the well-supported hot, dense early phase from which the universe expanded and cooled, or to the mathematical singularity reached, when classical general relativity is extended backward beyond the conditions where it can be trusted. Observations strongly support the hot early universe through cosmic expansion, ancient background radiation, and the measured abundance of light elements. They do not allow scientists to observe the supposed first instant directly. The singularity is therefore not a photographed moment of creation. In modern relativity, a singularity is more accurately understood as a place where paths through space-time cannot be continued, and the theory stops providing a complete physical description. As the universe is mathematically traced backward, its temperature and density rise until quantum effects of gravity should become unavoidable. No experimentally confirmed theory currently describes that regime. General relativity explains gravity and large-scale spacetime extremely well, while quantum theory explains microscopic matter with extraordinary accuracy, but applying both under the earliest extreme conditions remains an unfinished task. This means science does not presently know whether time truly began, passed through an earlier phase, or emerged from a state in which familiar ideas of duration did not apply. One possibility is that time has a genuine lower boundary. In that case, every physical clock, every change, and every causal process would begin with the universe. Asking what caused that beginning in an earlier moment would be difficult because cause normally requires temporal order. One event occurs, then another follows. If no earlier time existed, the usual meaning of cause might not reach beyond the boundary. This does not prove that the universe appeared without explanation. It means that an explanation, if one exists, may not resemble an event occurring previously. A law can describe an entire pattern without acting at an earlier date, just as the rules defining a geometric shape do not need to be applied one corner before another. Some quantum cosmology proposals explore a beginning of this kind. In the Hartley-Hawking no-boundary proposal, the earliest universe is represented by a smooth quantum geometry without a sharp past edge. Ordinary time would emerge only as the universe entered a more classical expanding phase. The proposal does not say that people could travel into a region where time literally becomes another ordinary direction, and it has not been confirmed by observation. It is a mathematical attempt to replace a violent initial singularity with a geometry that closes smoothly rather than terminating at a crude first instant. The no-boundary idea remains influential but disputed, with unresolved questions about how its probabilities should be defined and whether it predicts a universe resembling the one observed. A very different possibility is that the Big Bang was not the beginning of time, but a transition. In loop quantum cosmology, simplified quantum models of the universe can replace the classical singularity with a bounce. A previous cosmos contracts, reaches an extreme but finite state, and then begins expanding. Time continues through the transition, so there is a meaningful earlier phase, although it may look nothing like the universe around you. Researchers have studied whether such a bounce could leave subtle patterns in primordial radiation, or the large-scale distribution of matter, but no decisive observational signature has established that it occurred. The theory also faces open questions about how closely its simplified cosmological models follow from a complete theory of quantum gravity. Other scenarios propose cycles of expansion and contraction, an emergent universe that existed in a nearly static state before expanding, or a larger inflationary setting in which our hot Big Bang was the beginning of one region rather than the beginning of all reality. Yet extending expansion indefinitely into the past is not automatically possible. The Borda-Girth-Vilenkin theorem shows that many spacetimes with positive average expansion cannot be continued indefinitely along certain past-directed paths. This does not prove that reality began from absolute nothing. nor does it rule out every eternal model. It shows that inflation alone usually cannot supply a complete past, and that some additional physics is needed at its boundary. The competing possibilities reveal an important distinction. Time before our hot early universe and time before all physical reality are not the same question. There may have been a pre-Big Bang phase, while time itself stretches farther back. Or the expanding universe may have emerged from a quantum condition where ordinary temporal language loses meaning. Time might even be an emergent property rather than a fundamental ingredient. In some approaches to quantum gravity, the deepest equations do not contain time in the familiar form used by everyday physics. Change in temporal order may arise from relationships between parts of the universe. Much as temperature arises from the collective motion of many particles, even though one isolated particle does not possess temperature in the same way. If time is emergent, the earliest universe might not have been frozen in an endless instant. It may have existed in a form for which earlier, later, and how long were not yet meaningful descriptions. This idea is difficult because every thought you form unfolds in sequence. Language places one word after another. Memory arranges experiences into order. An explanation normally moves from cause to consequence. You are trying to understand the possible origin of time with a mind that cannot think outside time. Even the word before secretly carries the structure you are questioning. Science deals with this limitation by replacing intuition with models and asking what each model predicts. A useful theory must eventually connect the unknowable early regime with observable evidence in the universe today. It might predict a particular pattern in primordial gravitational waves, unusual correlations in cosmic background radiation, or a measurable feature in the distribution of galaxies. Without such evidence, elegant origin stories remain possibilities rather than discoveries. Current observations allow scientists to reconstruct an extraordinary amount of cosmic history, but the closer they approach the earliest fraction of existence, the more their conclusions depend on untested high-energy physics. The honest position is therefore neither that time certainly began, nor that something definitely happened beforehand. Both claims go beyond what has been established. What can be said is that the everyday picture of an empty timeline existing before the universe is not demanded by physics. Time is affected by gravity, bound to spatial geometry, and measured through physical change. Remove the physical structure that supports clocks, trajectories, and causal relationships, and the meaning of time itself becomes uncertain. Perhaps there was an earlier contracting cosmos. Perhaps the universe has a smooth quantum origin without a first sharp second. Perhaps a future theory will reveal a form of reality deeper than time from which temporal order emerged. Or perhaps the classical boundary truly marks the beginning of every physically meaningful when. You are accustomed to believing that every beginning must have something waiting behind it. But that expectation was learned inside a world where time already exists. At the foundation of the cosmos, the rule may fail. The earliest boundary may not conceal an older yesterday. It may be the place where yesterday first became possible, where duration awakened with expansion, and where the universe did not begin at a moment in time so much as begin the existence of moments themselves. The universe may be shaped like a giant donut. If you could travel forever in one perfectly straight direction, the most surprising destination might be the place where your journey began, without turning around, reaching an edge, or passing through any visible doorway. This is the idea behind the possibility that the universe has a toroidal topology, often simplified as saying that space may be shaped like a giant donut. The phrase is memorable, but it can also be misleading. Scientists are not suggesting that the cosmos is a solid ring floating inside a larger empty room, with galaxies scattered across its outer surface and a physical hole through the middle. A toroidal universe would be defined by how distant regions of space connect to one another, not by how the universe looks from somewhere outside it. There may not even be a meaningful outside position from which its complete shape could be viewed. To understand the proposal, picture a world existing on a flat screen. When a traveler exits through the screen's right edge, the traveler immediately reappears at the left edge. Leaving through the top returns the traveler through the bottom. The surface has no boundary, yet it contains a limited amount of area. Now extend the same principle into 3 dimensions. Opposite faces of an enormous cosmic region could be connected, so anything crossing one face would continue through the opposite face without experiencing a break. The result is called a 3 torus. It can be finite while remaining locally flat, meaning that small regions would obey the familiar geometry you observe around you, even though the universe's overall connectedness would be very different. General relativity constrains the local curvature of space, but the equations do not uniquely determine its global topology, so measurements showing that space is close to flat do not prove that it must extend infinitely. This distinction between curvature and topology is essential. A floor can be flat, whether it is an endless plane or a repeating surface whose opposite boundaries are connected. In the same way, 2 universes could possess almost identical local geometry, while differing completely in overall size and connectedness. One could be infinite, while another could be finite and wrap around itself. If the cosmos had this repeating structure, a beam of light traveling far enough might circle through space and eventually return from another direction. You could theoretically look outward and see multiple images of the same galaxy, because its light had reached you along different routes. Those copies would not necessarily look identical. Light taking a longer route would show the galaxy at an earlier stage of its development, so one object might appear in several parts of the sky at different cosmic ages. In an extremely compact universe, some distant objects could even be ancient images of regions located much closer to us than they appear. The night sky would then resemble a hall of mirrors without any physical mirrors, filled with repeated views produced by the connectedness of space itself. Astronomers have searched for this effect, but identifying repeated galaxies is difficult because galaxies evolve, merge, rotate, and may be partly hidden by dust. The clearest test instead uses the cosmic microwave background, the ancient radiation arriving from every direction. Because this radiation comes from a distant spherical shell surrounding us, a sufficiently small repeating universe could cause that shell to intersect copies of itself. The intersections would appear as pairs of circles in different parts of the sky, carrying matching temperature or polarization patterns. Researchers call these matched circles, and finding a convincing pair would provide powerful evidence that space wraps around. Planck satellite searches found no reliable sign of a compact toroidal topology on scales smaller than roughly the observable region examined, placing strong limits on how small such a universe could be. This negative result does not establish that space is infinite. It tells us that if the universe wraps around in a relatively simple way, the repeating scale is probably too large for obvious copies to appear within the observable cosmos. A topology larger than the distance light has been able to cross could remain completely hidden from us. You cannot detect a cosmic loop if no signal has had enough time to travel around it. The observable universe is only the region from which light has reached us, not necessarily the whole universe, so the global structure may extend far beyond the part available to telescopes. Some more complicated topologies can also avoid producing the simple back-to-back circle patterns used in early searches, leaving a broader range of connected spaces observationally possible than a casual reading of the results might suggest. Even the word donut hides an important complication. The familiar donut you can hold is a two-dimensional surface bent through three-dimensional space. A 3 torus is a three-dimensional space with repeating directions, and representing it visually would normally require an additional dimension. Scientists do not need that extra surrounding dimension to be physically real. The topology can be described internally through the rule that opposite regions are identified. From inside such a universe, you would not encounter a curved wall marking the place where space reconnects. Stars would not suddenly stretch as they passed through a seam, and spacecraft would not feel a jolt when crossing from one side to another. There would be no special boundary, because the boundary would exist only in the simplified diagram used to represent the connections. Every location could feel ordinary. This is what makes cosmic topology so difficult to detect. The global shape may govern the longest possible journeys while leaving every nearby experiment unchanged. It is similar to living on Earth without knowing the planet is round. A small patch of ground appears flat, and only observations across great distances reveal that paths eventually reconnect. The comparison is useful, though Earth's surface is curved while a 3 torus can be locally flat. If the universe were toroidal, it might also possess preferred repeating lengths. Space could wrap around at different distances in 3 directions, producing something more like an elongated cosmic box than a symmetrical donut. More complex versions could involve twists or rotations, so crossing a connected boundary might return an object with its orientation changed relative to the original coordinate system. There are several mathematically possible compact flat topologies, and the simple cubic torus is only the easiest to describe. Researchers test these models by looking not only for repeated circles, but also for subtle correlations in ancient radiation that would not be expected in an infinite, simply connected space. So far, none has produced evidence strong enough to overturn the standard assumption that the observable region can be treated as part of a much larger, simply connected cosmos. Yet that assumption remains practical rather than finally proven. The question also carries an unusual consequence for the meaning of cosmic size. An infinite universe contains endlessly more space, while a toroidal universe could have a finite volume without possessing an edge. There would be no final wall, no last galaxy standing beside an abyss, and no location where space suddenly stopped. Asking what lies beyond the universe would become unnecessary, because every direction would remain inside it. A traveler could continue indefinitely while repeatedly crossing the same global space, just as someone can walk around Earth forever without reaching the end of its surface. The traveler's path could be endless, even though the available space was finite. This separates distance traveled from the amount of unique territory that exists. It also raises the possibility that sufficiently long journeys would return not only to familiar places, but to the same physical region approached from another direction. In reality, such a voyage would be far beyond any conceivable technology, and the universe's changing conditions would complicate the journey enormously. The value of the idea is not that humans might one day fly around the cosmos and arrive home from the opposite side. Its value is that it forces science to distinguish between what observations show and what intuition assumes. You look into the sky and naturally interpret different directions as leading toward different regions. But if space is multiply-connected, paths that seem to diverge could eventually meet. 2 patches of sky that appear unimaginably far apart might belong to routes through the same underlying cosmic domain. The universe could contain fewer unique places than its visible depth suggests, while presenting those places through several paths of light. There is currently no evidence that this is the actual architecture of the cosmos, and describing it as a giant donut should never be mistaken for an established discovery. It is one scientifically legitimate possibility among many, constrained but not completely eliminated by observations. The simplest small toroidal models have become unlikely because the expected repeating patterns have not appeared, while versions larger than the observable universe may remain impossible to confirm with present data. That leaves humanity in a peculiar position. We can measure the geometry of nearby space, map ancient radiation across the sky, and test whether distant patterns repeat. Yet the complete connectedness of the universe may lie permanently beyond the horizon of observation. Space may extend without limit, curve back through another geometry, or close upon itself through connections too large for light to reveal. Matter and antimatter should have cancelled each other out. Everything in your body may exist because the early universe failed to balance its accounts by roughly 1 particle in a billion. For nearly every particle of matter, nature provides an antimatter partner with the same mass but opposite electrical charge. The electron has the positron, the proton has the antiproton, and entire antiatoms can be assembled from these reversed ingredients. Antimatter is not fictional, negative mass, or matter traveling visibly backward through time. It is produced naturally in some radioactive processes and cosmic ray collisions, and scientists manufacture small quantities of it in particle accelerators. When a particle meets its corresponding antiparticle, the pair can annihilate, converting their mass into other forms of energy and new particles, commonly including high-energy light. If the young universe produced matter and antimatter in exactly equal amounts, nearly every particle should eventually have found an opposite partner, leaving behind a cosmos dominated by radiation rather than stars, planets, oceans, and living bodies. Yet the universe around you is overwhelmingly made of matter. The antimatter half that might have been expected is absent on cosmic scales, and no complete explanation has yet shown why. The leading picture is surprisingly delicate. The early universe may have contained almost equal quantities, but for approximately every billion antimatter particles, there was about one additional matter particle. After the matched particles annihilated one another, that tiny excess survived. Every ordinary atom visible today may descend from that narrow remainder. The existence of galaxies can therefore be understood not as the result of matter winning an evenly matched battle through strength, but as the amplified consequence of an almost invisible imbalance. A difference so small that it would seem irrelevant in a laboratory became decisive when repeated across the entire cosmos. To understand how such an imbalance could form, physicists look for places where nature treats matter and antimatter slightly differently. If every physical process occurred as a perfect mirror image, equal beginnings would continue producing equal outcomes. But certain unstable particles do not obey that perfect symmetry. Their decays can occur at slightly different rates or follow different patterns from the decays of their antiparticles. This phenomenon is called charge parity violation, usually shortened to CP violation. The term describes a failure of nature to remain completely unchanged when particles are replaced by antiparticles and spatial directions are reflected. It was first discovered in particles called kaons during the 20th century and was later observed in several other particle systems. These differences are real, repeatedly measured, and included in the standard model of particle physics. Yet the known amount of CP violation is far too small to explain the enormous cosmic dominance of matter. The standard model contains part of the necessary story, but apparently not enough of it. In 2025, the LHCb experiment at CERN reported the first conclusive observation of CP violation in the decay of a baryon, the same broad family of particles that includes protons and neutrons. Researchers compared more than 80,000 decays of a short-lived particle called the Beauty Lambda baryon with the corresponding decays of its antimatter partner and found a measurable difference. This was an important expansion of where matter-antimatter asymmetry has been observed, but it did not solve the cosmic mystery. The measured effect remains compatible with known physics and is still nowhere near sufficient to explain why the universe retained so much matter. Scientists therefore suspect that an additional process operated during the universe's earliest stages, creating what is called baryogenesis, the generation of an excess of baryons, the particles that later formed atomic nuclei. In 1967, physicist Andrei Sakharov identified three broad ingredients that such a process would require. First, interactions must sometimes change the total number of baryons. Otherwise, a universe beginning with equal quantities could never develop a lasting excess. Second, matter and antimatter must be treated differently through violations of certain symmetries. Third, the universe must temporarily fall out of thermal equilibrium because perfect equilibrium tends to erase differences as quickly as they appear. These conditions do not reveal which event created the imbalance. They function more like requirements that any successful explanation must satisfy. Several possibilities have been proposed. Electroweak baryogenesis suggests that the imbalance formed while the early universe changed state as it cooled, somewhat as water changes structure when it freezes, though the cosmic transition would involve fundamental fields rather than molecules. Expanding boundaries between regions in different states might have created conditions where matter and antimatter interacted unequally. However, measurements of the Higgs boson and known particle behavior make the simplest versions of this idea difficult to realize. More elaborate models introduce new particles or fields that have not yet been detected. Another possibility, called leptogenesis, begins not with protons and neutrons but with leptons, the particle family containing electrons and neutrinos. Hypothetical heavy neutrino-like particles might have decayed unevenly into matter and antimatter forms, producing an early imbalance among leptons. Known high-temperature processes could then have converted part of that imbalance into the baryon excess from which ordinary matter later formed. This proposal is attractive because neutrinos already behave in unusual ways. They have tiny masses, change type while traveling, and may contain clues about physics beyond the standard model. But the heavy particles required by many leptogenesis models have not been observed, and scientists do not yet know whether neutrinos violate CP symmetry strongly enough to explain the universe. Other theories place the origin of the imbalance at far higher energies, where unknown grand unified forces may have allowed massive particles to decay slightly more often into matter than antimatter. Some connect baryogenesis to undiscovered dark sector particles, while others explore whether new phases of fundamental fields or previously unknown violations of symmetry could have tipped the balance. None has gained decisive experimental confirmation. The difficulty is that the crucial process may have occurred at energies far beyond those accessible to present accelerators, during conditions that vanished long before atoms or stars existed. Scientists must search for indirect fingerprints, rare particle decays, differences in neutrino behavior, tiny electric distortions inside particles, unusual Higgs interactions, or new particles appearing in collider experiments. Each measurement removes some possibilities while leaving others alive. Antimatter itself is studied with extraordinary precision because even a minute difference between a particle and its antiparticle could reveal a missing law. Experiments trap antiprotons and antihydrogen, compare their masses, charges, magnetic properties, spectra, and response to gravity, and look for discrepancies. So far, matter and antimatter appear astonishingly similar in these fundamental properties. CERN reports that antihydrogen measurements and proton-antiproton comparisons have reached extremely high precision without exposing the dramatic difference needed to explain cosmic survival. This makes the mystery sharper rather than weaker. Antimatter falls under gravity as expected, carries opposite charge, forms anti-atoms, and follows nearly the same rules as matter. Nothing about an individual antiproton announces that its kind was destined to disappear from the cosmos. The decisive distinction may lie only in rare transformations that occurred under extreme early conditions. Nor is the missing antimatter likely to be quietly hiding in distant galaxies in amounts equal to matter. If large regions of matter and antimatter bordered one another, their boundaries should generate intense radiation as particles met and annihilated. Astronomical observations have not revealed the widespread signals expected from a nearby universe, divided into enormous matter and antimatter domains. Small amounts of antimatter still exist and are continually produced. But this is secondary antimatter created by energetic events, not evidence of an equal antimatter cosmos concealed beyond ordinary sight. The mystery is therefore not simply where all the antimatter went. Most of it probably annihilated. The real question is what created the tiny surplus that remained before annihilation completed its work. That surplus also teaches an important lesson about the meaning of symmetry in physics. Symmetry sounds like beauty and perfection, but a perfectly symmetric early universe might have been sterile. If matter and antimatter had followed one another with absolute equality, there may have been no durable material from which complexity could form. The existence of structure required nature to depart slightly from balance. Mountains, cells, books, memories, and every human face may owe their presence to an ancient imperfection so subtle that physicists are still struggling to reproduce it in their equations. This does not mean the universe intended to create life, nor that the imbalance was arranged for your arrival. It means only that a small physical asymmetry can grow into consequences no observer at the beginning could have recognized. You are not made from the dominant half of an originally unequal universe. You may be made from what was left after almost everything cancelled. Quantum mechanics allows two particles to share one fate. Two particles can be separated so completely that no signal could pass between them in time, yet their measurements can still fit together more closely than any local pre-written plan allows. This phenomenon is called quantum entanglement, and it does not mean that particles communicate through a secret beam, read one another's minds, or carry matching answers prepared in advance. It means that after certain particles interact or are created together, quantum mechanics may describe them through one shared state rather than through two fully independent sets of properties. You can move the particles far apart, but the theory continues to treat their measurable outcomes as parts of the same physical relationship. Suppose a laboratory creates two entangled photons and sends them toward detectors in opposite directions. Each detector can measure a property such as polarization, which describes how the photon responds to differently oriented filters. When one photon is measured, its result appears individually unpredictable. The other result is also unpredictable, but when researchers later compare many pairs, they discover correlations that depend precisely on how the two detectors were oriented. The individual answers look random, yet the combined pattern is highly ordered. This is the first important correction to the phrase, sharing one fate. Entanglement does not usually make both particles display one predetermined result. It links the probabilities governing their results so deeply that neither particle can always be given a complete independent description before measurement. A classical comparison can make this sound less strange than it is. Place a left glove in one box and a right glove in another, then send the boxes to opposite sides of Earth. Opening one box instantly tells you which glove is in the other, but nothing mysterious has happened. Both gloves possess their identities from the beginning, and you merely uncovered information that was already settled. Einstein hoped entangled particles might work similarly. Perhaps each particle carried hidden instructions telling it how to respond to every possible measurement, preserving the comforting idea that distant objects possess their own local properties and cannot influence one another faster than light. Physicist John Bell discovered a way to test whether this explanation could reproduce quantum predictions. He derived limits, now called Bell inequalities, that any broad class of local hidden instruction theories must obey. Quantum mechanics predicted that entangled particles could violate those limits. Experiments developed by John Clauser, Alan Aspect, Anton Zeilinger, and many others repeatedly found the stronger correlations predicted by quantum theory, work recognized by the 2022 Nobel Prize in Physics. Later experiments closed major weaknesses that had allowed critics to imagine that missed particles or unnoticed communication might be producing the results. In a landmark 2015 test, electron spins associated with defects in diamonds were entangled across approximately 1.3 kilometers, and the experiment violated a Bell inequality while closing the central detection and locality loopholes. These results do not prove that one particle sends an instantaneous command to the other. They show that nature cannot be explained by the simple picture in which each particle carries a complete set of local, predetermined answers, independent of how distant measurements are chosen. At least one assumption behind that classical picture must fail. Quantum theory captures this by assigning the pair a shared state whose correlations cannot be divided into two separate private realities. When the particles are measured, the relationship produces coordinated statistics, even though each local outcome remains random. That randomness is why entanglement cannot be used to transmit a message faster than light. A researcher measuring the first particle cannot choose the result that appears. They may obtain one outcome or another, but they cannot control the sequence to encode words. The distant researcher sees another random sequence and cannot determine, from those results alone, whether the first particle has even been measured. Only after the two researchers exchange their records through ordinary communication do the hidden correlations become visible. That comparison cannot travel faster than light, so relativity remains protected. The particles share a quantum relationship, but they do not provide an instant telephone across the universe. This distinction matters because popular descriptions often say that measuring one particle immediately changes the other. That language can be useful, but it suggests a clear signal moving from one object to the next, which experiments do not reveal. Quantum mechanics predicts the correlations without identifying a message passing through space. In many interpretations, the pair should be regarded as one extended system until measurement, even when its parts are widely separated. The strange feature is therefore not necessarily that information races between two independent objects. It may be that nature never gave those objects completely separate properties in the first place. Distance separates their locations, but not every aspect of their physical description. Entanglement is also more fragile than the phrase shared fate suggests. Particles do not remain perfectly entangled under all conditions forever. Interactions with stray light, heat, nearby atoms, measuring devices, or other environmental systems can spread the original relationship into countless surrounding degrees of freedom. This process, called decoherence, makes the useful entanglement difficult or impossible to observe. The surrounding world effectively gathers information about the system, and the clean two-particle relationship becomes diluted into a much larger network. This is one reason ordinary objects do not appear in obvious entangled states during daily life. Their enormous numbers of particles are continuously interacting with the environment. Laboratories must isolate quantum systems, cool them, control electromagnetic noise, and perform measurements quickly enough to preserve delicate correlations. Entanglement is not supernatural glue immune to physical disturbance. It is a specific structure in a quantum state, and maintaining it requires extraordinary control. Scientists can create it in several ways. A single high-energy photon can interact with specially designed material and produce two lower-energy photons whose properties are entangled. Atoms can become entangled after exchanging light. Superconducting circuits can share quantum states through controlled microwave interactions. Even particles that never met directly can become entangled through a process called entanglement swapping. In that procedure, two separate entangled pairs are created. One particle from each pair is brought together and jointly measured. Under the correct conditions, the two particles that remained apart, particles with no shared past interaction, become entangled. The procedure does not rewrite history or create a usable influence backward through time. It changes the way the remaining measurement outcomes are correlated once the full records are compared. Still, it demonstrates that entanglement belongs to relationships established by the entire experimental arrangement, not merely to a permanent thread attached when two particles touch. This relational structure enables quantum teleportation, another phrase easily misunderstood. Quantum teleportation does not transport matter, bodies, or energy instantly from one place to another. It transfers the quantum state of one system onto a distant system by using previously shared entanglement, a local measurement, and ordinary classical communication. The original state is destroyed during the process, so it is not copied, and the receiver cannot reconstruct it until the necessary classical information arrives. Nothing moves faster than light, but a state can be transferred without researchers learning its full unknown details. This ability has become important in plans for quantum networks, where entanglement could help connect processes, distribute quantum states, and verify secure communication. Entanglement is also one of the central resources of quantum computing. Classical bits store one of two definite values, while quantum bits can be prepared in states whose joint description grows far richer when they become entangled. A quantum computer does not simply try every answer in separate hidden universes and return the correct one. Its algorithms carefully manipulate amplitudes and correlations so that unwanted possibilities interfere destructively while useful outcomes become more likely. Entanglement allows the state of the whole processor to contain relationships that cannot be reproduced efficiently by treating each quantum bit independently. It does not guarantee that every problem becomes easy. A noisy entanglement can destroy a computation rather than improve it. But for particular tasks, Controlled quantum correlations may provide advantages unavailable to ordinary machines. Entanglement can also strengthen security through methods known as device-independent quantum cryptography. Because Bell inequality violations cannot be reproduced by simple local predetermined instructions, sufficiently well-controlled correlations can help certify that outcomes contain genuine private randomness, even when some details of the equipment are not trusted. Any eavesdropper attempting to gain information may disturb the correlations or reduce the observed violation. Real systems still face practical weaknesses, losses, and engineering challenges. So the word quantum does not automatically make communication perfectly secure. The faster you move through space, the slower you age. A journey fast enough could carry you centuries into Earth's future, while only a few years passed for your own body. Not because speed freezes life, but because motion changes the amount of time different travelers experience. This is one of the most precisely tested consequences of Einstein's special theory of relativity. In ordinary life, everyone seems to share the same seconds because human speeds are tiny compared with the speed of light. But as an object moves faster relative to an observer, the interval measured by the moving clock becomes shorter than the interval measured by the observer's clock. From Earth, a rapidly moving spacecraft would appear to age more slowly. Its clocks would tick less, its computers would run more slowly, and every chemical and biological process inside it would unfold at the same reduced rate. The traveler would not feel slowed down. Their heartbeat, thoughts, hunger, and wristwatch would all seem completely normal, because everything within the spacecraft would be progressing together. Only when the traveler compared clocks with someone who followed a different path through space-time would the difference become undeniable. This effect is called time dilation, and it is not an illusion caused by signals taking longer to reach the eye. Correcting for the travel time of light still leaves a real disagreement in the elapsed time recorded by the clocks. The reason begins with a fact that nature refuses to negotiate. Every observer moving steadily measures the same speed of light in a vacuum, regardless of how quickly the source or observer is moving. This is unlike ordinary motion. If a car throws a ball forward, someone beside the road measures the ball's speed as the car's speed plus the throwing speed. Light does not behave that way. A beam emitted from a moving spacecraft is still measured at the same universal speed by the traveler and by an observer on Earth. To preserve that rule, distance and duration cannot remain identical for everyone. Observers in relative motion divide space and time differently, and moving clocks accumulate less time between shared events. The universe does not contain one master clock that all travelers must obey. Each object carries its own elapsed time along the route it takes. This can be demonstrated with a simple clock made from light. Picture a pulse bouncing vertically between two mirrors. To someone traveling beside the clock, the light follows a straight path up and down. To someone watching the clock move past, the mirrors shift sideways while the light travels, so the pulse follows a longer diagonal path. Because both observers must measure the same speed of light, the outside observer concludes that each bounce requires more time. The moving clock therefore ticks more slowly. A mechanical clock, an atomic clock, and a living body must follow the same rule, because otherwise different kinds of clocks would disagree about physical events, and the laws of nature would depend on the mechanism used to measure them. Time dilation affects all processes, not merely the hands of a clock. Nature has demonstrated this through particles called muons. Muons are produced when high-energy cosmic rays strike Earth's upper atmosphere. They are unstable and, when at rest, decay so quickly that most should disappear before reaching the ground. Yet large numbers are detected at Earth's surface because they travel close to the speed of light. From our perspective, their internal decay clocks run slowly, allowing them to cross much more atmosphere than their ordinary lifetime would permit. From the muon's perspective, its lifetime remains normal, but the atmosphere is shortened in the direction of motion. Both descriptions predict the same detection results, and experiments confirm them with great precision. Human-built clocks show the effect as well. Highly accurate atomic clocks flown on aircraft or carried on satellites return with slightly different readings from clocks that remained on the ground. Speed is not the only influence, because gravity also changes elapsed time, so researchers must account for both effects. Even after those corrections, the measured differences match relativity. This is not merely a laboratory curiosity. Satellites in global navigation systems carry atomic clocks moving rapidly around Earth while also experiencing weaker gravity than clocks on the surface. Their speed makes them tick slightly more slowly, while the weaker gravity makes them tick more quickly. Engineers must correct the combined difference. Otherwise, location errors would accumulate rapidly and navigation systems would lose useful accuracy. Every time a phone calculates a position from satellite signals, it quietly relies on a universe in which time is not the same everywhere. The dramatic human consequence is often illustrated by the twin paradox. One twin remains on Earth while the other travels in a spacecraft at a speed close to that of light, turns around, and returns. The spacefaring twin comes home younger than the twin who stayed behind. At first, this may seem contradictory because motion is relative. From the spacecraft, Earth appears to be moving. So why should the traveler age less? The two situations are not fully symmetrical. The traveling twin changes direction and switches between different states of motion in order to return, while the earthbound twin follows a different, more direct path between departure and reunion. In relativity, different paths through space-time can contain different amounts of elapsed time. Acceleration explains why the traveler's situations differ, but the age gap is not produced only during the brief turnaround. Most of it accumulates during the long periods of high-speed travel. The crucial fact is that the twins leave together, reunite later, and can place their clocks side by side. Once reunited, everyone agrees about which clock recorded less time. Imagine a spacecraft that could maintain a speed extremely close to the speed of light. A voyage to a distant star might require many years as measured from Earth, but much less time for the passengers. Push the speed closer still, and a traveler could cross distances that seem impossibly large within a human lifetime, while thousands or millions of years passed in the rest frame of Earth. This would function as one-way travel into the future. The traveler would not vanish and reappear instantly, nor would they reverse time. They would simply experience less duration than people who remained behind. When they returned, the civilization they knew might have transformed or disappeared, while they themselves had aged only modestly. Relativity permits this in principle, but engineering makes it extraordinarily difficult. An object with mass cannot be accelerated to the speed of light because each further increase in speed requires more energy, and the required energy grows without bound as the object approaches that limit. Even reaching a significant fraction of light speed would demand enormous amounts of energy. Collisions with sparse gas atoms and dust grains would become dangerous, producing intense radiation and releasing large amounts of energy against the spacecraft. Accelerating gently enough to protect passengers, carrying fuel, shielding the vehicle, and slowing down at the destination would add further challenges. Time dilation is real, but it does not provide an easy machine for escaping the present. It also cannot be used to preserve someone by making them move at everyday speeds. A passenger on an airplane technically ages less because of motion than a person standing still relative to the ground. But the difference is unimaginably small, far less than a blink across a normal flight. Astronauts aboard the International Space Station travel around Earth at thousands of kilometers per hour, and therefore accumulate slightly less time from motion than people on the surface, though gravitational effects must also be considered. After months in orbit, the net age difference is measured in tiny fractions of a second, not years. Relativistic aging becomes dramatic only at speeds far beyond current crewed spacecraft. Another important detail is that there is no absolute state of rest. You are moving with Earth as it rotates, traveling around the Sun, and moving with the solar system through the galaxy. But relativity does not say that all this motion automatically slows you relative to a hidden stationary universe. Time dilation is defined through comparisons between particular observers and paths. During steady relative motion, each observer can describe the other's clock as running slowly because they disagree about which distant events occur simultaneously. There is no contradiction while they remain separated. A definite age difference becomes measurable when they reunite or otherwise compare clocks through a clearly defined physical procedure. This is why the statement, "the faster you move, the slower you age," is useful but incomplete. Faster relative to whom and compared along which journey? Without those details, speed alone does not assign a universal aging rate. What remains invariant is the time measured by your own clock along your path. You always age normally from your perspective, second by second. But another traveler following a different path may reach the same reunion, having experienced a different number of seconds. This changes the meaning of age in a subtle way. Age is not simply how long the universe has existed while you are present. It is the duration accumulated by your body along its particular route. Two people can share the same departure and reunion, yet carry different amounts of history within them. Light from the edge of the observable universe left before Earth existed. Some of the light entering your eyes tonight began its journey before the Sun, Earth, or any human atom had taken its present form. Looking into deep space is not like looking across an ordinary landscape, because light does not deliver the universe to you instantly. It moves extraordinarily fast, but the distances between galaxies are so enormous that even light may spend billions of years crossing them. The moon appears to you as it was a little more than 1 second ago. Sunlight shows you the sun roughly 8 minutes in the past. The nearest stars are seen years earlier, while distant galaxies appear as they existed millions or billions of years before the present day. A telescope is therefore not only an instrument for seeing farther through space, it is also a machine for seeing deeper into history. When astronomers observe a galaxy whose light has traveled for 10 billion years, they are not seeing that galaxy as it exists now. They are receiving an ancient message emitted when the universe was much younger and Earth had not yet formed. The galaxy may have changed completely since then. Its stars may have died, new generations may have appeared, and it may have collided with neighboring galaxies. Yet none of that later information has had enough time to reach us. The sky is not a live picture of the cosmos. It is a layered archive in which every distance reveals a different age. This becomes especially strange near the limit of the observable universe. That limit is not a physical wall standing at the end of space. It is the boundary of what has had enough time to send information to us since the early universe became transparent. There may be vastly more universe beyond it, but its light has not reached Earth and may never reach us, so those regions remain outside our observable world. The oldest light humans can detect directly is the cosmic microwave background, a faint radiation filling the entire sky. It was released about 380,000 years after the beginning of the hot early universe, when matter had cooled enough for electrons and atomic nuclei to join into neutral atoms. Before that transition, free charged particles scattered light so frequently that the universe behaved more like a glowing fog. Photons could not travel far without being redirected. Once atoms formed, much of the light was finally able to move freely across space. Those photons have been traveling ever since, carrying an image of the universe when there were no stars, no planets, and no galaxies in their mature forms. They began their journey more than 9 billion years before Earth formed. What arrives today is not light from a shell of material still sitting at the distance where it emitted the radiation. While the photons traveled, space itself expanded, increasing the separation between us and the regions that released them. Their present distance is therefore much greater than the simple number of years they spent traveling. This is why the observable universe is far wider than 13.8 billion light-years, even though its age is about 13.8 billion years. The regions whose ancient light reaches us today are now estimated to be roughly 46 billion light-years away in every direction, giving the observable universe a present diameter of about 93 billion light-years. This does not mean the light traveled faster than light. It means the space through which it traveled stretched while the journey was underway. The photons continued moving locally at the normal speed of light, but the distance between cosmic regions changed around them. Expansion also stretched the light itself. Photons released in the early universe once had far shorter wavelengths and much higher energy. As space expanded, their wavelengths lengthened until the radiation cooled into the microwave range detected today. Astronomers call this cosmological redshift. It allows them to estimate how much the universe has expanded since particular light was emitted. The farther into the cosmos they observe, the more strongly the light is generally shifted toward longer wavelengths, and the earlier the chapter of cosmic history they uncover. Deep observations reveal young galaxies that look smaller, more irregular, and more active than many nearby galaxies. They contain stars forming rapidly from relatively unprocessed gas, showing scientists how cosmic structure developed rather than presenting the universe as a finished creation. Yet distance also makes interpretation difficult. A remote galaxy may appear faint, not only because it is far away, but because its light has been stretched, absorbed, scattered, or shifted outside the range visible to human eyes. Astronomers use infrared, radio, X-ray, and other instruments because much of the ancient universe is invisible to ordinary vision. A region that appears dark to your eyes may be filled with old light that the eye simply cannot detect. Even powerful telescopes do not see all the way back to the first moment. Electromagnetic radiation cannot provide a clear image from before the universe became transparent, because the early cosmic fog repeatedly scattered it. Scientists instead search for other messengers, such as primordial gravitational waves or subtle patterns preserved in background radiation, though no direct detection has yet opened a confirmed view of the earliest instance. The visible history of the universe therefore begins not at an absolute beginning, but at the oldest surface from which light could travel freely. Everything beyond that surface is hidden from ordinary telescopes, not necessarily because nothing was there, but because light had not yet become an effective messenger. This means that the phrase, "the edge of the observable universe," describes an edge in information rather than an edge in existence. You stand at the center of your own observable universe simply because every direction is measured from your position. An observer in a distant galaxy would stand at the center of a different observable region, overlapping partly with yours, but including places you cannot see. There is nothing physically special about your location. Every observer is surrounded by a horizon created by the finite age of the cosmos and the travel time of information. This horizon also changes. As time passes, light from some previously unseen regions may finally reach us, adding new information to the observable universe. But cosmic expansion creates another effect. Some extremely distant galaxies are being carried away so rapidly by expanding space that light they emit today may never reach. Earth. We can see their ancient light because it began traveling when they were closer and cosmic conditions were different. Yet we may never observe what they are doing now. Their visible image can continue aging slowly, while their later history slips permanently beyond communication. In that sense, astronomy sometimes studies objects that remain visible only through messages sent from a past with which we can no longer exchange new information. You may be seeing the childhood of a galaxy whose present has become unreachable. This does not mean the galaxy has crossed a solid border or broken the speed limit. The changing geometry of the expanding universe can place its future signals beyond our cosmic horizon. The night sky is therefore filled not only with distance, but with separation in time and information. Every photon is evidence that an event happened somewhere else, long before the evidence arrived. Some photons were emitted when dinosaurs lived on Earth. Others began traveling before the first animals, before the first complex cells, or before the planet itself existed. By the time one reaches a telescope, the source may be unrecognizable compared with the image encoded in the light. You never observe a distant object and its current state at the same time. You observe a relationship between its past and your present. This is why astronomers can reconstruct cosmic development by examining different distances. Nearby galaxies provide relatively recent views, while increasingly distant ones reveal progressively earlier eras. Scientists cannot watch one galaxy evolve for billions of years, but they can compare many galaxies seen at different ages. arranging them like pages from separate copies of the same long history. From those comparisons, they learn when stars formed most rapidly, how galaxies grew, how heavy elements accumulated, and how enormous structures emerged from a much smoother early universe. Light becomes a fossil that has traveled rather than remained buried. Its wavelength, brightness, spectrum, and direction preserve information about the source and about everything encountered along the way. Gas clouds absorb particular wavelengths, revealing their chemical composition. Gravity bends distant light, exposing otherwise invisible concentrations of mass. Expansion stretches it, recording the changing scale of the cosmos. A photon reaching Earth may therefore carry several histories at once: the history of the object that emitted it, the matter it crossed, and the universe through which it traveled. Yet the message is never complete. Light reveals only what interacted with it, and only from the moment it departed. You cannot use an ancient photograph to know what a person is doing today, and you cannot use billion-year-old light to know the present condition of a distant galaxy. This limitation is not a defect in telescopes. It is built into causality. Information requires time to travel, so the universe cannot be observed in one universal present. The farther you look, the less the word now applies. A telescope aimed into deep space gathers many pasts simultaneously. A nearby star from years ago, a remote galaxy from billions of years ago, and background radiation from an era before stars had begun to shine. A spoonful of neutron star would weigh 1 billion tons. A teaspoon taken from a neutron star would not sit quietly in your hand. It would carry roughly the mass of a mountain, crushing everything beneath it before anyone could even understand what had arrived. The popular claim that a spoonful would weigh 1 billion tons is a rough comparison rather than one exact number, because neutron star density changes from the outer crust to the deep interior, but the central idea is scientifically sound. Matter inside these stars is compressed to densities almost impossible to reproduce anywhere else in the universe. A neutron star forms when a massive star reaches the end of its usable nuclear fuel. For most of its life, the star survives through a balance between gravity pulling inward and pressure generated by nuclear reactions pushing outward. Once the core can no longer produce enough supporting pressure, gravity gains control. The core collapses with extraordinary speed, while the outer layers may be expelled in a supernova explosion. During the collapse, atoms lose the structure that makes ordinary matter spacious. Electrons are driven into protons, producing neutrons and neutrinos. The result is an object containing more mass than the Sun, packed into a sphere only about the size of a city. A typical neutron star may measure roughly 20 to 25 kilometers across, yet its mass can exceed that of the Sun. If the Sun were compressed to a similar density, it would fit inside a region small enough to cross by car in less than an hour, though no ordinary road or vehicle could survive there. The density is so great because atoms are mostly empty space. In normal material, the nucleus occupies only a tiny portion of an atom's volume, while electrons exist in much larger surrounding regions. The solidity you feel when touching a table does not come from atoms being packed like solid marbles. It comes mainly from electromagnetic interactions and quantum rules preventing matter from passing freely through itself. Inside a collapsing stellar core, gravity becomes powerful enough to overcome much of this ordinary atomic structure. Nuclei are forced into close contact, and matter begins to resemble an enormous atomic nucleus made mostly of neutrons. This is why even a tiny volume contains such enormous mass. A spoonful of water contains countless atoms separated by relatively large distances at the nuclear scale. A spoonful of neutron star material would contain nearly the same basic particles compressed until the gaps between atomic nuclei had almost disappeared. The result is not simply heavy metal or extremely hard rock. It is a state of matter governed by pressures, densities, and quantum effects that have no everyday equivalent. Neutrons cannot all occupy the same internal state, and their resistance to being forced together creates neutron degeneracy pressure. Repulsive effects from the strong nuclear interaction also become important at very short distances. Together, these effects can resist gravity and prevent further collapse, but only up to a limit. If the remnant is too massive, even neutron pressure may fail, and the object can continue collapsing into a black hole. A neutron star therefore exists in a narrow contest between gravity and quantum physics. Gravity attempts to compress the star into something smaller, while the microscopic behavior of particles prevents unlimited crowding. Every moment of the star's existence is the continuation of that balance. Its surface would be unlike any ground you know. The outermost atmosphere may be only centimeters thick, and below it lies a crust of atomic nuclei and electrons, compressed into a rigid lattice. Deeper down, increasing pressure drives nuclei into progressively more neutron-rich forms. Eventually, neutrons begin leaking out of nuclei and moving through the crust. Near the base, matter may organize into strange shapes often called nuclear pasta, because simulations suggest structures resembling sheets, tubes, and tangled strands. The humorous name hides serious physics. These forms may be among the strongest known materials because nuclear forces bind them under crushing pressure. Below the crust lies a core whose exact composition remains uncertain. It may contain a superfluid of neutrons, superconducting protons, and perhaps more exotic particles produced at extreme density. Some theories allow hyperons, particles containing strange quarks, while others suggest that neutrons may dissolve into a dense form of quark matter. Astronomers cannot dig into a neutron star or return a sample, so they infer its interior by measuring mass, radius, cooling, rotation, gravitational effects, and the behavior of stars that collide. These observations help rule out some models of dense matter while leaving several possibilities open. The phrase, "a spoonful weighs 1,000,000,000 tons," can make the material sound like an object that could somehow be removed and placed on Earth, but that picture is misleading. Neutron star matter exists in its extreme form because the star's gravity and pressure hold it there. If a small amount could somehow be separated from the star, it would no longer be under the same confinement. Free neutrons outside stable nuclei are unstable, and the compressed material would rapidly transform, expand, decay, and release enormous energy. It would not remain as a neat, spoon-shaped lump of ultra-dense substance. The process of removing it would be impossible with known technology long before stability became the main concern. The gravity near the surface of a neutron star is billions of times stronger than gravity on Earth. Anything approaching would be accelerated to tremendous speed. A falling object would release an enormous amount of energy upon impact, and tidal forces could stretch or destroy it, depending on the star's mass and the distance involved. The surface escape speed can be a large fraction of the speed of light, meaning that even leaving the star requires an energy no ordinary spacecraft could provide. The phrase "weigh 1,000,000,000 tons" also needs careful interpretation. Mass is the amount of matter, while weight depends on gravity. A teaspoon of typical neutron star material might have a mass on the order of hundreds of millions to several billion metric tons, depending on which density is assumed. On Earth, that mass would exert a weight corresponding to the gravitational pull on billions of tons of material. But if it somehow appeared here, its effects would not resemble a heavy object placed on a scale. It would fall through the ground, generate intense pressure, disturb surrounding material gravitationally, and likely undergo violent physical changes. The comparison is useful because it translates density into familiar language, but reality would be far more destructive and complex than the image of a spoon bending under a heavy sample. The same compression that gives neutron stars their density also produces extraordinary gravity across the entire object. Light leaving the surface loses energy as it climbs away, so radiation is gravitationally redshifted. Time also passes slightly differently near the star compared with far away, though the effect is not as extreme as near a black hole. Mountains on a neutron star, if they exist, may rise only millimeters or centimeters because gravity flattens the crust so efficiently. A feature that would count as a small bump by human standards could still contain an enormous mass. The star's surface is expected to be remarkably smooth, not because nothing disturbs it, but because any large irregularity is pressed down by gravity. Yet even tiny deformations matter. A rapidly spinning neutron star with a slight asymmetry could emit gravitational waves, carrying energy away through ripples in space-time. Detectors search for these continuous signals because they may reveal the strength of the crust and the star's internal structure. Neutron stars can also rotate with astonishing speed. Some complete hundreds of turns each second. Their immense density allows them to spin so rapidly without flying apart, though there is still an upper limit beyond which rotation would overcome gravity at the equator. Their magnetic fields can be trillions of times stronger than Earth's, and in magnetars, the field becomes more extreme still. These fields can distort atoms, guide charged particles, and power bursts of high-energy radiation visible across the galaxy. None of this comes from density alone, but density creates the compact environment in which rapid rotation, powerful gravity, and intense magnetism combine. A neutron star may begin with the mass and angular momentum of a much larger stellar core. As that core shrinks, its rotation accelerates, much as a spinning skater turns faster when pulling in their arms. Magnetic fields can also become concentrated during collapse. The final object is therefore not simply a dead star. It is a compressed engine storing rotational, magnetic, thermal, and gravitational energy in a volume small enough to fit inside a major city. Pulsars reveal this hidden activity. A pulsar is a rotating neutron star whose magnetic axis is misaligned with its rotation axis. Beams of radiation sweep through space, and if one crosses Earth, telescopes detect a regular pulse. Some pulsars rival the precision of atomic clocks over long periods, although their rotation can gradually slow and occasionally jump in events called glitches. These sudden changes may occur when a superfluid inside the star transfers angular momentum to the crust. A glitch lasting only a brief moment can provide evidence about matter buried kilometers beneath a surface no instrument can touch. Scientists learn about the interior by watching the star's rotation hesitate and correct itself. Sound can levitate objects without touching them. A small object can hang in mid-air with no string, no magnet, and no visible support, held only by carefully arranged sound waves pressing against it from every side. This is called acoustic levitation, and it works because sound is not merely something you hear. Sound is a traveling pattern of pressure moving through a material such as air, water, or another medium. When powerful sound waves are aimed toward one another, they can form a standing wave, a stable pattern containing regions where the pressure changes very little and regions where it changes strongly. Tiny objects placed in the right locations can become trapped near these stable points, called nodes, because the surrounding acoustic pressure pushes them back whenever they begin to drift away. The object is not floating because gravity has disappeared. Gravity is still pulling downward, but the upward force produced by the sound field can balance its weight. In many laboratory systems, ultrasonic transducers are used to create the waves. Ultrasound has a frequency above the range of human hearing, allowing researchers to generate strong, precisely controlled pressure patterns without filling the room with an unbearable tone. By adjusting the timing and strength of many transducers, scientists can move the pressure nodes, carrying small beads, droplets, insects, or biological samples through the air without touching them. This is more difficult than simply making something hover. The sound field must remain stable, and the object must be small and light enough for acoustic forces to overcome gravity. A heavy object requires far more intense sound, and increasing the power creates new problems, including heating, turbulence, instability, and possible damage to delicate material. Acoustic levitation, therefore, does not provide an easy way to lift people, cars, or buildings. Its greatest value lies at much smaller scales, where avoiding physical contact can be extremely useful. A liquid droplet can be suspended without resting against a container, allowing scientists to study chemical reactions without contamination from a vessel's walls. Molten materials can be cooled while floating, helping researchers observe how crystals form when no surface is present to trigger solidification. Pharmaceutical compounds can be examined in unusual states, and biological cells or small organisms can be positioned gently for imaging and experimentation. In some devices, droplets can even be moved, merged, separated, and mixed by reshaping the acoustic field, creating a kind of contactless laboratory in which sound performs the work of tiny mechanical tools. The force involved is often described as acoustic radiation pressure. The name may sound as though sound itself is a form of radiation like light, but here it refers to the steady force produced when waves transfer momentum to an object. Each pressure variation is brief, yet repeated interactions create an average push. The object's shape, size, density, and surface all affect how it responds, while the wavelength of the sound determines what can be trapped efficiently. If the object is too large compared with the wavelength, the field becomes more complicated and stable levitation becomes harder. Researchers can overcome some limitations by arranging many individually controlled sound sources in phased arrays. These systems shape the wavefronts electronically, allowing pressure traps to form in different locations without physically moving the speakers. A computer can alter the phases of the transducers and make a particle travel along a path, rotate, or join another particle. This is similar in principle to steering a beam through coordinated timing, but the object is guided by pressure rather than by a solid mechanism. More advanced setups can create several traps at once, manipulating multiple objects independently. Acoustic levitation also works in liquids, although the forces and wave behavior differ because liquids are denser than air. In medical research, related acoustic forces can guide particles, sort cells, concentrate substances, and move microscopic material through fluid channels. This field, often called acoustofluidics, may help develop diagnostic tools that handle biological samples with less physical contact and fewer moving parts. Sound can also influence tiny objects through surface acoustic waves traveling across solid materials, giving engineers another way to control droplets and cells on miniature devices. These techniques do not make matter weightless. They exploit the fact that waves carry momentum and can create structured forces when precisely arranged. The same broad principle appears in optical trapping, where focused light can hold microscopic particles, but acoustic methods can often exert stronger forces on larger objects and may be gentler for certain biological materials. Still, acoustic levitation has strict limits. Strong ultrasound can heat tissue, create cavitation in liquids, or generate intense pressure that damages fragile samples. A levitated object may oscillate, deform, spin, or escape if the field changes unexpectedly. Even air currents can disturb small particles. Engineers must therefore design the frequency, geometry, and power carefully, especially when working with living cells or volatile liquids. The spectacular appearance of a floating object can make the technology seem like a violation of gravity, yet the real explanation is more instructive. Levitation occurs because forces that are normally too small or disorganized to notice have been concentrated into a stable pattern. Sound waves are usually scattered through rooms, reflected from surfaces, and absorbed by materials, so their pressure does not support visible objects. In a controlled acoustic chamber, those same waves are aligned until their combined effect becomes strong enough to compete with weight. The object then rests in a pocket of pressure that has no solid walls but behaves like a three-dimensional trap. You cannot see the trap, yet its existence can be mapped by measuring the field or watching how particles respond. This reveals that support does not always require contact. A hand holds an object through direct pressure, but a wave can distribute pressure through space and create an invisible equilibrium. The floating bead is not escaping physics. It is demonstrating physics with unusual clarity. Gravity pulls it downward, sound pushes it upward, and stability emerges where the forces balance. What appears like magic is actually an engineered negotiation between motion and pressure. The deeper lesson is that sound has always been physical, even when you experience it only as hearing. Every voice slightly presses against surfaces. Every musical note transfers energy through the air. Those forces are normally far too weak and unfocused to lift anything you can see. But when sound is intensified, synchronized, and shaped with precision, it can become a tool capable of holding matter without touching it. A silent-looking object suspended above a table is therefore not floating in emptiness. It is resting inside an invisible architecture of pressure, supported by waves moving too quickly for your eyes, and often too high for your ears. And in that suspended moment, sound reveals a side of itself that hearing alone can never show. It is not only information traveling through space, but a physical force that can reach into space, gather around matter, and hold it there. The human eye can detect a single photon in total darkness. In a room sealed from every lamp, screen, star, and doorway, the faintest possible visitor may still be enough to disturb a cell in your eye. One photon, a single indivisible packet of light. The claim that a human can see one photon sounds almost impossible, and the most honest version is more subtle than the headline. Scientists know that an individual rod photoreceptor can respond to the absorption of a single photon, but whether that microscopic event can reliably rise through the retina and become a conscious human perception remains an active scientific question. A photon carries so little energy that ordinary detectors often require careful cooling and electronic isolation to distinguish it from background noise. Yet the dark-adapted eye contains biological machinery capable of operating near that same physical limit. Rod cells are responsible for most vision in very dim conditions. They do not provide the detailed color perception associated with cone cells, but they are extraordinarily sensitive, especially in regions away from the exact center of your gaze. Inside each rod are molecules of rhodopsin, a light-sensitive pigment. When one photon is absorbed, it can change the shape of one rhodopsin molecule and begin a biochemical chain reaction that affects many other molecules before altering the rod's output. This amplification is why one tiny event can become large enough to matter, and the response is surprisingly consistent for a process beginning with a single molecule. Researchers have directly measured single photon responses in rod cells and identified specialized retinal circuits that preserve these weak signals while reducing other forms of cellular noise. But sensitivity comes with a difficult cost. The visual system must separate real photons from events generated inside the eye itself. Rhodopsin can occasionally change spontaneously, even when no light is present, creating a signal resembling the absorption of a photon. Other cells introduce their own fluctuations as they transmit information. In perfect darkness, you therefore do not possess a perfectly silent visual system waiting for light. You possess a detector listening through its own faint internal static. This biological background has sometimes been described as dark light because the eye can generate photon-like events without an external photon. The challenge is not merely detecting a weak signal, it is deciding whether that signal came from the world or from noise. Early experiments in the 1940s tested dark-adapted observers with extremely weak flashes and concluded that only a small number of photons needed to be absorbed by the retina for a person to report seeing light. Many more photons had to be sent toward the eye because some were reflected, absorbed by the cornea and lens, or missed the sensitive pigment entirely. The successful photons were spread across many rods, making it unlikely that any one rod absorbed more than one. These experiments helped establish that night vision reaches the scale of individual quantum events, even if conscious detection usually depends on several such events occurring close together. The experience itself would not resemble a bright point shining clearly in darkness. Near the threshold of vision, perception becomes uncertain. You may feel that something happened without being able to describe a shape, color, or exact location. This is why researchers do not simply ask, "Did you see it?" A person might say yes when nothing was presented, or remain cautious when a real signal occurred. Instead, carefully designed experiments may present two time intervals and ask which interval contained the light, even if the sensation is too weak to describe confidently. Repeated choices can reveal whether performance rises above random guessing. In 2016, researchers used a quantum light source that generated photon pairs. Detecting one photon allowed them to know when its partner had been sent toward a participant's eye. Subjects sat in darkness, received 2 possible time intervals, and selected which interval they believed contained the photon. Across the post-selected single-photon trials, the overall correct choice rate was 51.6%, only slightly above the 50% expected from guessing, while answers marked with the highest confidence were correct about 60% of the time. Most correct responses were nevertheless given with low or medium confidence. The authors presented the results as the first evidence that humans can directly perceive a single photon incident on the cornea, while also estimating that only a small fraction of delivered photons actually generated a retinal signal. That experiment is fascinating, but it should not be turned into the strongest statement that anyone can enter a dark room and clearly watch individual photons arrive. The measured advantage was tiny, depended on thousands of trials, trained participants, precisely controlled timing, careful placement of the stimulus on a rod-rich part of the retina, and statistical selection of events likely to contain one photon. The person was not identifying a visible object with ordinary certainty. At best, the study suggested that on rare occasions, the visual system may discriminate the faint consequence of a single photon from its own background activity. The result also attracted debate over the statistical methods and whether the evidence was strong enough to support the conclusion. More recent work has added another important complication. Study examining primate retinal output and matching human visual tasks found evidence that the pathway used for detection in darkness applies a threshold that discards many single photon responses. According to this model, the signals reaching the relevant output cells often require the near coincidence of 2 or more photon absorptions within a large pool of rods. The retina may sacrifice the ability to transmit every isolated photon in order to prevent random internal noise from constantly producing false alarms. This means the eye's first sensory cell may register one photon while conscious vision does not. The distinction is essential. Detection can occur at several levels. A molecule may react, a rod may change its output, a retinal circuit may transmit the event, the brain may distinguish it from noise, and the person may finally report that something was seen. Proving the first step does not automatically prove the last. The visual system is not designed to celebrate every microscopic signal. It must decide which events are trustworthy enough to influence behavior. If every spontaneous molecular fluctuation became a visible flash, darkness would be filled with false stars generated inside your own eyes. By filtering aggressively, the retina reduces these false alarms, though it may also erase genuine solitary photons. That trade-off reveals why biological sensitivity is not simply a contest to respond to the smallest possible amount of energy. A useful sensory system must balance sensitivity against reliability. Seeing an imaginary predator every few seconds would be as dangerous as missing a real one. The eye therefore operates through thresholds, convergence, and comparison. Signals from many rods feed into shared pathways, allowing several weak events to combine. But this convergence also removes precise detail. This is one reason night vision is sensitive, yet less sharp than daylight vision. A single rod may know that one photon arrived, but the larger system may demand supporting evidence before allowing that event into awareness. Your own behavior reveals some of these adaptations. After entering darkness from a bright environment, you initially see almost nothing because the systems used in daylight remain adapted to stronger illumination. As the eye adjusts and rod sensitivity becomes more influential, faint objects gradually emerge. You may also notice a dim star more easily when you look slightly beside it rather than directly at it, because the center of the retina is specialized for detailed cone vision, while rod density is greater farther away. None of this allows you to count photons individually, but it shows that the eye changes strategy as light becomes scarce. Under bright conditions, precision, color, and speed matter. Under starlight, sensitivity matters more, and the retina begins combining information across wider areas and longer intervals. The boundary of vision is therefore not fixed like the minimum brightness setting on a machine. It depends on adaptation, retinal location, stimulus duration, wavelength, attention, expectation, and the criterion a person uses before admitting that something was seen. A cautious observer may miss more real flashes but report fewer false ones. A less cautious observer may detect weaker signals while also claiming to see light during blank trials. At the edge of perception, seeing becomes a decision made under uncertainty rather than a simple switch between darkness and light. This makes the single photon question valuable far beyond vision. It allows scientists to study how a nervous system handles the weakest signal permitted by physics. The photon cannot be divided into a smaller portion of visible light and still remain a photon. Once one is absorbed, the eye either captures that event or it does not. The retina must amplify a discrete microscopic occurrence, preserve it across several layers of cells, compare it with spontaneous noise, and decide whether the evidence is strong enough to matter. The process exposes the meeting point between quantum physics and conscious experience, without requiring exaggerated claims that the eye behaves like a perfect laboratory detector. It does not. Many photons entering the eye are lost. Many absorbed photons fail to influence perception, and many internal events imitate light. The universe is not only expanding, it is accelerating. The universe is not merely becoming larger, it is becoming harder for gravity to slow down, as though the distance between the great structures of the cosmos has entered a race that keeps gaining momentum. This does not mean galaxies are firing engines and accelerating through a pre-existing emptiness. On the largest scales, space itself is expanding, causing sufficiently distant galaxies to become separated even when they are not actively moving through their local surroundings. Gravity still binds atoms, holds your body together, keeps Earth orbiting the Sun, and preserves galaxies and many galaxy groups. The acceleration becomes important only across the enormous distances where matter is spread thinly, and the expansion of space can dominate. A ruler inside your room does not lengthen, and the space between you and the chair does not steadily grow, because electromagnetic forces and gravity overwhelm the extraordinarily weak cosmological effect at that scale. But between distant collections of galaxies, where no stronger binding force keeps everything together, the amount of space can increase, carrying those systems farther apart. For much of scientific history, astronomers assumed this expansion should gradually slow. The universe contains matter, matter produces gravity, and gravity attracts. Even if the cosmos began by expanding rapidly, its own contents seemed destined to act like a brake. The great question appeared to be whether the braking would be strong enough to stop expansion and cause a future collapse, or too weak to prevent the universe from expanding forever at an ever-decreasing rate. Then, near the end of the 20th century, two independent research teams tried to measure that slowing and found almost the opposite. They studied distant Type Ia supernovae, stellar explosions whose light curves can be standardized well enough to estimate their true brightness. Once astronomers know approximately how luminous such an explosion really was, they can compare that value with how faint it appears and infer its distance. The color and spectrum of its light also reveal how much cosmic expansion has stretched its wavelengths. Distance tells researchers how far away the event was, while redshift helps describe how much the universe has expanded since its light began traveling. By comparing supernovae across different distances and therefore different eras, scientists can reconstruct parts of the universe's expansion history. The distant explosions appeared dimmer than expected in a universe whose expansion had been steadily slowing. They were farther away than the earlier models predicted, implying that the expansion had begun accelerating. The discovery was so transformative that Saul Perlmutter, Brian Schmidt, and Adam Rees received the 2011 Nobel Prize in Physics for the observations that revealed the accelerating universe. The result did not depend forever on one set of exploding stars. Later evidence came from several independent approaches, including patterns in the ancient cosmic radiation, the growth and clustering of galaxies, gravitational lensing, and a feature called baryon acoustic oscillations. In the early universe, matter and radiation carried pressure waves through a hot cosmic plasma. When the universe cooled, those waves left behind a slight preference for galaxies to be separated by a particular enormous distance. Astronomers can measure how the apparent size of this pattern changes at different stages of cosmic history, using it as a kind of standard ruler. Supernovae provide a distance ladder based on brightness, while baryon acoustic oscillations provide a ruler written into the distribution of galaxies. The fact that several techniques support an accelerating expansion makes it extremely difficult to dismiss the discovery as a simple error in one type of object. Yet the word accelerating still causes confusion. It does not necessarily mean that the numerical expansion rate measured at any one moment must continually rise. In the standard cosmological model, the Hubble rate, the amount of recession per unit distance, can decrease while expansion is still accelerating. The distinction lies in what happens to the distance between widely separated, unbound objects. Consider a car that is moving forward while its speed falls from 100 kilometers per hour to 90, then to 85, then to 82. It is slowing. Now consider a car whose speed rises from 50 to 60, then to 65, then to 68. It is accelerating, even though the amount added each time becomes smaller. Cosmic acceleration concerns the behavior of the universe's overall scale. The separation between sufficiently distant points grows in a way that speeds up rather than being pulled toward a halt. The universe can therefore have a changing Hubble rate while still possessing accelerated expansion. This detail matters because the cosmos is not behaving like an explosion whose fragments simply coast through static space. Its geometry evolves, and the relationships between distance, time, matter, and energy determine how that evolution proceeds. The simplest successful explanation adds a component called dark energy. The name does not identify a known substance. It labels whatever is responsible for the observed acceleration within our current description. Under the standard model, dark energy accounts for roughly 68% of the universe's total matter-energy content, while dark matter and ordinary matter make up most of the remainder. This estimate is not obtained by placing dark energy in a container and weighing it directly. It emerges from fitting a cosmological model to several observations. The leading version treats dark energy as a cosmological constant, meaning that empty space possesses a small constant energy density. This idea has a peculiar consequence. Matter becomes increasingly diluted as the universe expands because the same amount of matter occupies a growing volume. Radiation thins out even faster because its wavelengths are also stretched. A constant vacuum-like energy, however, does not dilute in the same way. Each unit of space retains the same tiny energy density, so as more space appears, the total amount associated with that component increases. This should not be pictured as fuel being manufactured inside a box, or as a violation that allows useful energy to be extracted freely. In general relativity, defining the total energy of an expanding universe is not as straightforward as counting energy inside an unchanging container. The essential point is that a component whose density remains nearly constant can become increasingly influential as matter spreads out. Long ago, the universe was denser, and the gravitational attraction of matter dominated the cosmic behavior. Expansion continued, but it slowed. As matter became more diluted, dark energy's relative influence grew. Roughly 5 billion years ago, according to the standard picture, the balance shifted far enough for accelerated expansion to begin. NASA describes the transition as occurring around 9 billion years after the universe began. Dark energy is sometimes called repulsive gravity, but this phrase can make it sound like an invisible wind pushing directly on galaxies. Nothing has been observed streaming outward from the centers of cosmic voids, and no nearby detector feels a dark energy breeze. The effect emerges through the way a smoothly distributed energy component influences space-time on large scales. In general relativity, pressure contributes to gravity as well as energy and mass. A component with sufficiently negative pressure can produce accelerated expansion. Negative pressure does not mean ordinary suction, and it does not behave like pressure inside a tire. It describes how the energy responds as space expands. A cosmological constant possesses exactly the type of pressure needed to generate the observed acceleration. The equations can describe this remarkably well, but they do not explain why empty space should carry that particular tiny amount of energy. Quantum theories suggest that fields contribute energy even in their lowest states, yet straightforward attempts to connect those contributions with the observed cosmological value produce an enormous disagreement. The measured acceleration is small enough to allow stars and galaxies to form, but it is not zero. Explaining why the value lies where it does remains one of the deepest unsolved problems in fundamental physics. Another possibility is that dark energy is not constant. It could be associated with a field that changes slowly over cosmic time, gaining or losing influence as the universe evolves. Different versions receive names such as quintessence, but none has been experimentally confirmed. The acceleration could also reveal that the theory of gravity requires modification across distances far larger than the solar system or even a galaxy. General relativity has passed demanding tests in many environments, yet the scales involved in cosmic acceleration are so vast that researchers continue asking whether an incomplete understanding of gravity might mimic the effect attributed to a new energy component. These explanations are difficult to distinguish because they can sometimes produce nearly identical expansion histories while predicting subtle differences in how galaxies cluster, how gravitational lensing bends light, or how cosmic structures grow. If dark energy acts as a smooth background, it changes expansion while gravity still gathers matter into structures. Modified gravity may alter both expansion and the rate at which structures form. This is why modern surveys do not merely measure how far galaxies are from one another. They map their positions, motions, shapes, and statistical patterns across billions of years. Neutron stars spin hundreds of times per second. During a single ordinary blink, the fastest known pulsar can turn dozens of times, sweeping its radiation across space with a rhythm so rapid that human senses could never separate one rotation from the next. Some neutron stars rotate hundreds of times every second, and the fastest securely measured radio pulsar, PSRJ 748-2468, completes 716 rotations per second, one full turn in roughly 1.4 milliseconds. That number is not a theoretical exaggeration. Astronomers detect its repeating radio signal, correct the arrival times for Earth's motion and the pulsar's binary orbit, and recover a rotation pattern more regular than almost any mechanical object humans could construct. A neutron star can rotate so quickly because an enormous amount of angular momentum is concentrated into a very small object. The basic principle can be felt when a spinning ice skater pulls their arms inward and begins turning faster. The skater has not created rotation from nothing. The same rotational momentum has been concentrated closer to the axis. When a stellar core contracts dramatically, its rotation can accelerate for the same reason. But this alone does not explain the fastest millisecond pulsars. Newly formed neutron stars can spin rapidly, yet strong magnetic fields and streams of energetic particles gradually carry rotational energy away, causing many young pulsars to slow over time. The speed champions usually follow a longer and stranger history. They are often old neutron stars living in binary systems, where a companion star eventually expands and begins transferring gas toward them. The gas does not fall straight down. It forms a rotating accretion disk, spiraling inward while carrying angular momentum. As that material joins the neutron star, it applies a continuing torque, turning the star faster little by little. Across a very long period, a neutron star that had once slowed can be spun back up until each rotation lasts only a few thousandths of a second. Astronomers call these objects recycled pulsars because a stellar companion has effectively given their rotation a second life. Observations of accreting systems and transitional pulsars support this evolutionary connection between matter transfer and millisecond rotation. The word recycled should not suggest that the star becomes young again. Its material remains ancient, but its rotation is renewed. By the time the transfer weakens or ends, the companion may have become a white dwarf, leaving behind a rapidly spinning pulsar that loses energy very slowly. These millisecond pulsars often have weaker external magnetic fields than younger pulsars, allowing them to preserve their speed for billions of years rather than breaking quickly. Their stability is so great that astronomers can predict the arrival of their pulses far into the future and identify delays smaller than a millionth of a second. Yet the signal is not created because the entire star repeatedly brightens and darkens. A pulsar's magnetic axis is usually tilted relative to its rotation axis. Charged particles are accelerated around the magnetic regions, producing narrow beams of radio waves, X-rays, gamma rays, or other radiation. As the star turns, those beams sweep through space. If one crosses Earth, telescopes record a pulse, much as a distant observer sees a lighthouse flash whenever its beam points toward them. A neutron star whose beam never crosses Earth may remain invisible as a pulsar even though it is rotating. Pulsation is therefore partly a matter of cosmic alignment. At 716 turns per second, a point near the equator would travel around the star tens of thousands of kilometers each second, reaching a significant fraction of the speed of light. The surface is not being carried faster than light, but it is moving so rapidly that relativity, the star's deformation, and the behavior of matter under extreme rotation all become important. Rotation prevents the star from remaining perfectly spherical. The equatorial region is pushed outward, while the poles are slightly flattened, producing an oblate shape. If the spin increased too far, gravity would no longer be able to hold material securely at the equator. The star would reach a mass-shedding limit, where additional speed could strip matter away or destabilize the entire object. The precise limit depends on the star's mass, radius, and internal response to pressure. So finding an even faster pulsar would immediately eliminate some proposed descriptions of neutron star matter. NASA notes that models can permit rotation rates considerably above the observed record, sometimes approaching about 1/500 rotations per second, depending on the star's properties, yet no confirmed pulsar has been found near that theoretical limit. This gap creates a scientific puzzle. If accretion can keep adding angular momentum, and many neutron stars should physically survive faster rotation, why does the observed population appear to stop near 700 turns per second? One possibility is that the incoming material eventually reaches a balance with the star's magnetic field. The rotating magnetic environment can interfere with the inner edge of the accretion disk, and once the star turns fast enough, the disk may no longer transfer angular momentum efficiently. The same interaction can even push material outward, acting as a brake. Another possibility is that rapid rotation creates tiny distortions or fluid oscillations that release energy through gravitational waves. The star might then radiate away additional angular momentum almost as quickly as accretion supplies it, settling into a natural speed limit below the point of physical breakup. Researchers have long studied whether unstable internal waves known as R modes, small crustal deformations, or other asymmetries could produce this braking effect. But no single explanation has been confirmed as the universal reason for the observed cutoff. Studies of accreting millisecond pulsars show that their measured spin distribution ends well below many estimated breakup frequencies, leaving magnetic torques, gravitational radiation, and the details of accretion as competing parts of the answer. A pulsar's rotation is therefore not only a spectacular number, it is a record of everything that has pushed or resisted the star across its lifetime. Matter falling inward can accelerate it. Magnetic fields can slow it. Particle winds carry energy away. A companion's orbit can change the apparent timing through motion toward and away from Earth. Even the interstellar medium delays lower frequency radio waves slightly more than higher frequency ones, so astronomers must remove the influence of ionized gas between the pulsar and the telescope. After accounting for these effects, the remaining changes become clues. Most pulsars gradually spin down, their periods lengthening by tiny amounts as rotational energy is lost. The change may appear insignificant from 1 second to the next, but precise observations across years reveal it clearly. From the rotation rate and its gradual decline, scientists estimate magnetic properties, energy loss, and a rough characteristic age, although that age is not always identical to the star's true history. The pulsar becomes a clock whose slowing exposes the invisible forces acting upon it. Sometimes that clock suddenly jumps. In an event called a glitch, a pulsar begins rotating slightly faster without warning, and then may slowly relax toward its previous trend. The increase can be extremely small compared with the total rotation rate. Yet it is obvious because the timing had been predicted so precisely. The leading explanation involves superfluid material inside the neutron star. A superfluid can rotate through many tiny quantized vortices, rather than as an ordinary rigid liquid. As the outer parts of the star gradually slow, some internal vortices may remain pinned and preserve more angular momentum. When many suddenly shift or unpin, angular momentum can be transferred to the observable outer region, producing the rotational jump. Glitches, therefore, turn a timing irregularity into a probe of an interior that cannot be examined directly. Models and observations connect these events with exchanges of angular momentum between internal superfluid components and the rest of the star, although the detailed trigger and the roles of different layers remain under investigation. Millisecond pulsars tend to glitch less dramatically than many younger pulsars, but their timing is not perfectly free of noise. Tiny irregularities can arise from changes in the star, its surroundings, its companion, the intervening plasma, or the instruments used to observe it. Astronomers must model all these effects before treating a pulsar as a precision clock. The best pulsars are not perfect because nothing physical is perfectly isolated. They are valuable because their imperfections can be studied and separated. When several stable millisecond pulsars across the sky are monitored together, they form a pulsar timing array. A passing gravitational wave can slightly alter the journey of their radio signals, causing characteristic advances and delays in pulse arrival times. One pulsar alone may show a disturbance that could be mistaken for noise, but a gravitational wave background should produce a related pattern across many pulsars, depending on their positions in the sky. These arrays are designed to detect extraordinarily slow gravitational waves with cycles lasting months or years, likely produced by populations of enormous black hole binaries. Modern timing array projects have reported evidence for a correlated low-frequency gravitational wave background, although researchers continue refining noise models and determining the exact astrophysical sources. The rapidly spinning star is therefore transformed into part of a detector larger than Earth. The brain can rewire itself after serious damage. A damaged brain can lose part of itself and still discover another way to speak, move, remember, or recognize the world, not by growing a perfect replacement, but by changing how its surviving networks work together. This ability is called neuroplasticity, the lifelong capacity of neural connections and larger brain systems to strengthen, weaken, reorganize, and sometimes assume new roles in response to experience or injury. After a stroke, traumatic injury, tumor removal, or other serious damage, some neurons may die permanently, so the phrase, "the brain rewires itself," must not be mistaken for complete regeneration. The lost tissue does not simply return, and recovery is never guaranteed. What can happen is more complex. Cells surrounding the injured area may alter their connections. Previously quiet pathways may become more active. Distant regions may change their contribution, and repeated practice may teach the remaining system to accomplish a task through a different route. Neuroplasticity is therefore not a hidden repair switch. It is a gradual process shaped by the location and size of the injury, the person's age and health, the abilities that were affected, the condition of the surviving pathways, and the type and amount of rehabilitation received. In the first hours and days after an injury, the visible disability may be caused by more than the neurons that were permanently destroyed. Swelling, inflammation, disrupted blood flow, chemical imbalance, and a phenomenon called diaschisis can temporarily reduce activity in areas that were not directly damaged but were connected to the injured region. A person may initially be unable to move an arm, understand speech, or focus attention, partly because an entire network has been shocked into dysfunction. As swelling decreases and surviving cells regain more normal activity, some ability can return spontaneously. This early improvement is not necessarily evidence that new circuits have already been built. Part of it may come from systems recovering from temporary suppression. Later progress depends increasingly on learning and reorganization. Connections that repeatedly participate in a successful movement or mental task can become more efficient, while pathways that remain unused may weaken. The old phrase, "use it or lose it," is incomplete, but it captures something important. Experience helps determine which networks the recovering brain preserves and strengthens. This is why rehabilitation is not merely exercise for weakened muscles. When a stroke survivor repeatedly reaches for a cup, forms a word, shifts weight while walking, or attends to one side of space, the nervous system receives thousands of opportunities to refine whatever surviving pattern can produce a better result. Task-specific practice is especially valuable because the brain adapts to what it is repeatedly asked to do. Practicing isolated strength may improve strength, but recovering the act of buttoning a shirt usually requires practicing the timing, sensation, attention, and coordinated movement involved in buttoning a shirt. Rehabilitation uses repetition, feedback, increasing difficulty, and meaningful goals to turn attempted actions into more reliable neural strategies. Stroke rehabilitation research and clinical guidelines treat experience-dependent plasticity as a central mechanism of recovery, while also emphasizing that treatment must be adapted to the individual rather than reduced to one universal exercise. The changes can occur at several levels. Individual synapses, the communication points between neurons, can become stronger or weaker. Surviving neurons may grow new branches and form additional contacts. Brain maps representing parts of the body can shift their boundaries. Regions near the injury may begin responding to movements they did not strongly represent before, while connected areas farther away can increase their involvement. If the main route controlling a hand has been partly damaged, secondary pathways may contribute more, although these replacements may produce less precise movement. Recovery can therefore involve both restoration and compensation. Restoration means rebuilding a function through patterns closer to those used before the injury. Compensation means finding another practical solution, such as using the unaffected hand, changing posture, relying on visual cues, or using a device. Compensation can restore independence quickly and may be essential, but it can also reduce opportunities for the impaired system to improve. If a person stops attempting to use a weakened arm because every failure is frustrating, the brain receives fewer reasons to preserve its remaining control of that arm. This can develop into learned non-use, in which the limb's biological capacity is greater than its role in daily life. Constraint-induced movement therapy was designed around this problem. Under professional supervision and for selected patients, use of the less affected limb is limited while the affected limb performs intensive tasks. The goal is not to punish compensation, but to create enough successful practice for the weakened network to become useful again. This therapy can help some people, but it is not appropriate for every injury or level of impairment, and excessive difficulty can create fatigue, pain, unsafe movement, or discouragement. Neuroplasticity responds to experience, but more intensity is not automatically better at every stage. Some evidence suggests that the period after stroke contains windows of heightened responsiveness, yet clinical research has shown that timing and dosage matter, and extremely intensive activity too early can sometimes be unhelpful. A major NIH-supported trial found particularly strong benefits from additional motor therapy begun roughly 2 to 3 months after stroke, while other studies show that meaningful improvement may continue much later, even though the average responsiveness to treatment generally declines over time. The popular belief that recovery ends after 6 months is therefore too rigid. The fastest changes often occur early, but chronic stroke survivors can still improve years later through sufficiently focused practice. Late progress may be slower, and require greater effort because habits have become established, biological growth conditions are less favorable, and daily life has reinforced compensatory strategies. Yet the adult brain does not become fixed like dry cement. Learning a skill after injury still alters networks, just as learning altered them before the injury. What changes is the difficulty of the task and the amount of surviving circuitry available to support it. Someone with a small injury affecting part of a motor region may regain nearly normal movement, while another person with extensive damage to major descending pathways may remain severely impaired despite excellent care. Motivation cannot recreate pathways that no longer exist, and describing every poor outcome as a failure to believe in recovery is both false and cruel. Effort matters because it supplies the experience that guides plasticity, but biology sets real limits. Fatigue, depression, pain, sleep problems, seizures, medication effects, sensory loss, and cognitive difficulty can all reduce the amount or quality of practice a person can sustain. Effective rehabilitation therefore often involves physical therapists, occupational therapists, speech-language pathologists, physicians, psychologists, nurses, and family members working on different parts of one interconnected problem. Movement cannot be separated entirely from attention, emotion, sensation, confidence, and the environment in which the movement is attempted. Language recovery shows how widely distributed this reorganization can become. Damage to language networks in the dominant hemisphere may produce aphasia, affecting speech, comprehension, reading, or writing without destroying intelligence. During recovery, tissue near the damaged language regions may regain activity. Remaining areas within the same hemisphere may become more efficient, and corresponding regions in the opposite hemisphere may participate. Greater activity on the opposite side is not always automatically beneficial. Sometimes it provides useful support, while in other cases it may reflect effort, inefficient compensation, or interference with recovering networks. The brain does not follow one simple rule in which the other half takes over. The best pattern depends on the injury and the stage of recovery. Repeated naming, conversation, reading, melody, gesture, and communication practice can help rebuild access to language, but progress may be uneven. A person may suddenly retrieve a word in one setting and lose it in another because the emerging pathway is not yet stable. Improvement often looks less like a switch turning on and more like a path through grass becoming clearer each time it is walked. The same principle applies to movement. Early attempts may be slow, inaccurate, and dependent on intense concentration. With repetition and feedback, the system can reduce unnecessary effort, coordinate muscles more effectively, and make the action less consciously demanding. Functional brain imaging can reveal changes in which regions are active during the task, but increased activity is not always proof of better recovery. An inefficient brain may recruit many areas because the task is difficult, while a more practiced brain may accomplish it with a smaller, more focused network. Scientists therefore combine imaging with actual measurements of function, rather than assuming that every colorful brain scan represents improvement. Plasticity can also become maladaptive. The brain strengthens repeated patterns, whether or not those patterns are desirable. Bees can see colors that are invisible to human eyes. A flower that looks uniformly yellow to you may display a dark, ultraviolet target to a bee, turning an ordinary petal into a landing map written in colors the human eye will never naturally see. Bees do not simply view a sharper or more colorful version of your world. Their vision divides light differently. Humans normally build color from receptors most sensitive to red, green, and blue regions of the spectrum, while honeybees use receptors tuned mainly to ultraviolet, blue, and green. Ultraviolet light lies beyond the violet edge of human vision, but to a bee it is part of ordinary color experience rather than a mysterious glow added on top of the visible world. At the same time, bees are relatively insensitive to the longer red wavelengths humans see clearly, so a purely red surface may appear very dark, unless it also reflects ultraviolet, or contrasts strongly with its surroundings. Their world is therefore not better or worse than yours. It is shifted. Some differences that are obvious to you may nearly disappear to them, while patterns hidden from you may become among the most noticeable features in a landscape. Behind each of a bee's compound eyes are thousands of small visual units called ommatidia. Each receives light from a slightly different direction, and the nervous system combines their signals into information about movement, shape, direction, and color. The result should not be imagined as a screen made of large hexagonal pixels, as popular illustrations often suggest. A bee's brain processes overlapping signals and extracts useful features from them, although its spatial detail is far lower than human visual detail. From far away, a bee may not see the fine lines on a petal at all. It first detects broad contrast, movement, scent, and the flower's separation from the green background. As it approaches, color patterns become more useful, helping it distinguish one flower from another and locate the rewarding center. Bee vision is adapted not for reading small letters or admiring distant scenery, but for flying quickly through a complex environment, avoiding obstacles, recognizing profitable plants, and returning efficiently to the colony. Its green-sensitive pathways can process rapid visual changes especially quickly, supporting motion detection during flight, while ultraviolet and blue signals contribute strongly to color discrimination. Many flowers take advantage of this sensory system. Pigments in their petals may absorb ultraviolet light in one region and reflect it in another, producing circles, lines, contrasting centers, or bullseye patterns that are invisible to unaided human eyes. Some of these patterns guide pollinators toward nectar, pollen, or the reproductive structures of the flower. A petal that appears evenly colored to you may look to a bee as though its center has been marked with an arrow. Experiments removing or altering floral markings have shown that such guides can change how pollinators approach, where they land, and how efficiently they find rewards. This benefits the bee by reducing search time, but it can also benefit the plant by positioning the insect where pollen is most likely to be collected or deposited. Yet not every ultraviolet marking is a simple nectar sign, and not every flower visited by bees carries a dramatic ultraviolet target. Floral patterns can serve several functions, and their importance depends on the plant, the pollinator, the surrounding vegetation, the lighting, and the distance from which the flower is viewed. Ultraviolet reflection is only one component of a richer visual display that may also include brightness differences, edges, symmetry, texture, gloss, shape, scent, and temperature. Scientists therefore avoid treating every UV photograph of a flower as proof of a secret message deliberately designed for bees. The patterns must be tested through behavior to learn whether bees notice them and whether they affect real visits. Bees are not born knowing the identity of every useful flower. They learn. A forager can associate a particular color, pattern, scent, shape, or combination of cues with a sugar reward. After successful visits, it becomes more likely to return to similar flowers, creating what is known as flower constancy. This tendency allows the bee to forage efficiently because it does not need to relearn how to handle a completely different flower at every stop. It also helps plants because pollen is more likely to be transferred between members of the same species rather than wasted on unrelated flowers. The preference is flexible rather than absolute. When rewards decline or another flower becomes more profitable, bees can change their choices. Their visual world is therefore shaped not only by photoreceptors, but by memory, expectation, effort, and reward. A color does not merely look different. It can carry a history. To one bee, a blue patch may predict a rich supply of nectar. To another, after different experiences, the same patch may mean little. Researchers test this learning by training bees to land on colored targets containing sugar, then presenting unrewarded choices to see which colors or patterns they remember. Such studies show that bees can distinguish many colors, compare patterns, generalize from familiar examples, and sometimes solve surprisingly complex visual tasks. But their decisions depend heavily on the conditions of the experiment, the size of the target, its background, the angle of approach, and whether the bee sees it while hovering or walking can all influence the result. This matters because animal vision cannot be understood simply by listing the wavelengths an eye detects. Vision is behavior. The important question is not only what light enters the receptors, but what information the animal can extract from it while moving through its natural world. Bees also demonstrate a form of color constancy. Sunlight changes throughout the day, clouds alter the balance of wavelengths, and a flower viewed in shadow reflects a different mixture of light than the same flower in direct sun. If every lighting change transformed a flower into an entirely new color, learned preferences would become unreliable. The bee's visual system compares information across the scene and partially compensates for changing illumination, allowing familiar flowers to remain recognizable under different conditions. This ability is not perfect, and extreme lighting can still alter choices, but it prevents the world from becoming visually unfamiliar whenever a cloud passes overhead. The color a bee uses is therefore not a simple property extracted from one petal. It is a relationship between the light reflected by the flower, the surrounding background, the state of adaptation in the eye, and the processing performed by the nervous system. A green leaf, a blue petal, and an ultraviolet reflecting center influence one another because contrast helps determine what becomes noticeable. Human photographers sometimes create bee vision images by recording ultraviolet, blue, and green reflections and assigning them false colors that a human screen can display. These images are useful for revealing patterns, but they are translations, not photographs of the bee's private experience. A human monitor cannot emit a sensation that lies outside human color vision, so ultraviolet information must be represented using a visible substitute. The image may show where ultraviolet is reflected, but it cannot tell you what ultraviolet feels like to a bee. Just as describing red to someone who has never possessed red-sensitive vision would not recreate the experience. Even calling ultraviolet a color can tempt you to picture a more intense violet, when it may occupy a perceptual category with no human equivalent. Bees combine signals from their 3 receptor types into color relationships unique to their nervous system. Some mixtures, such as light strongly stimulating ultraviolet and blue receptors together, may create distinctions for which human language has no natural name. The limitation belongs not to vocabulary alone, but to experience. You cannot imagine a new basic color simply by concentrating harder, because every color you picture is built from the visual system you already have. This makes bee vision a reminder that the visible spectrum is not a complete inventory of light. It is the section your biology translates into color. The electromagnetic world extends far beyond both ends of human sight, but different animals sample different portions according to their ecological needs. Many birds, butterflies, fish, reptiles, and insects detect ultraviolet, while some snakes sense infrared radiation through specialized heat-sensitive organs, rather than experiencing it through ordinary color vision. No creature receives the entire spectrum. Every sensory system selects. The bee's ultraviolet sensitivity is particularly useful because sunlight contains UV wavelengths that can reflect from flowers, leaves, wax, wings, and the sky. Even 2 petals that appear equally white to you may differ strongly to a bee if one reflects ultraviolet and the other absorbs it. This can allow bees to distinguish plant species or floral regions that would seem visually identical under human observation. Yet bees do not depend on ultraviolet alone. In some situations, a strong boundary visible through green contrast may guide them more effectively than color. Fine patterns must be large enough relative to the bee's visual resolution to be detected, and color becomes less reliable when targets are tiny or distant. A flower may therefore attract the bee through one feature from afar and reveal another feature during the final approach. Broad contrast draws attention, scent confirms identity, ultraviolet and visible patterns assist landing, and local cues guide the insect toward the reward. Plants communicate through underground fungal networks. Beneath a forest that appears silent, living threads finer than roots can connect one plant to another, carrying minerals, water, carbon compounds, and chemical changes through soil that looks empty from above. These threads belong to fungi, and many of them form intimate partnerships with plants known as mycorrhizae. The arrangement is ancient and practical rather than mysterious. A plant captures energy from sunlight and turns carbon dioxide into sugars and other carbon-rich compounds. But its roots cannot efficiently reach every pocket of phosphorus, nitrogen, or water hidden among soil particles. A fungus cannot manufacture sugar through photosynthesis, yet its microscopic filaments, called hyphae, can explore spaces too narrow and distant for roots to enter. At the root, the two organisms establish an exchange. The fungus supplies mineral nutrients gathered from the soil, and the plant provides carbon made in its leaves. Some fungi penetrate root tissues and form finely branched exchange structures inside plant cells, while others wrap roots in an outer sheath and grow between the cells. In both cases, the plant-fungus boundary becomes a busy trading surface rather than a simple point of attachment. The fungal network may extend far beyond the root's immediate nutrient-depleted zone, effectively increasing the volume of soil available to the plant. A single fungus can also colonize several roots, sometimes belonging to different plants or even different species. When this occurs, the plants are linked by what scientists call a common mycorrhizal network. The popular phrase "wood wide web" was created to describe this hidden connectivity, but it can make the network sound more human than it is. There are no conscious trees composing messages, no underground words, and no central operator deciding who deserves help. What exists is a physical system in which living organisms exchange resources, respond to changing conditions, and alter one another's behavior. That reality is already remarkable without giving the forest a human mind. The fungal partner is not a passive cable installed for the benefit of plants. It is an organism pursuing its own survival. It grows toward nutrient-rich areas, stores resources, changes the thickness and direction of its network, and allocates minerals among the roots that supply it with carbon. Laboratory experiments have followed fluorescently, tagged phosphorus moving through one fungal network toward separate host roots, and found that allocation can change over time and respond to the nutritional demand of the connected hosts. The network behaves less like a charity pipeline and more like a shifting biological marketplace in which supply, demand, location, and the value of each trading partner influence the movement of resources. A plant providing more carbon may sometimes receive more nutrients, but the outcome is not governed by one simple rule. A fungus may store phosphorus before releasing it, direct resources toward a route where the exchange is more profitable, or maintain several partners so that it does not depend entirely on one plant. The plants can also regulate the relationship. Roots may provide more carbon to fungal partners that deliver useful nutrients and reduce support to less beneficial fungi. This mutual exchange helps keep cooperation stable, but it does not guarantee fairness. Under some conditions, the fungus benefits the plant greatly. Under others, it may consume carbon while providing little in return. The relationship can shift along a spectrum from strongly beneficial to nearly parasitic, depending on soil fertility, temperature, moisture, plant species, fungal identity, and the life stage of each partner. A seedling in poor soil may gain enormously from fungal access to phosphorus, while a mature plant in nutrient-rich soil may pay more carbon than the partnership is worth. The same network can therefore support one plant, disadvantage another, and change its effect as the environment changes. This is important because the movement of a substance is not automatically the same as meaningful support. Scientists can label carbon in one plant, later detect some of that label in another, and establish that transfer occurred. But they must still determine how the carbon traveled, how much arrived, whether it entered useful plant tissue, whether the receiver gained any growth or survival advantage, and whether the donor deliberately supplied it. Carbon released into soil can be absorbed by microbes, converted into carbon dioxide, fixed again by another plant, or carried within fungal tissue without becoming a significant donation from plant to plant. Demonstrating movement is therefore easier than demonstrating purposeful sharing. One famous line of research found carbon moving between paper birch and Douglas fir seedlings associated with compatible fungi, helping inspire the image of trees redistributing food through a communal network. These experiments established that below-ground carbon transfer is physically possible, but later, scientific debate has emphasized that field results vary and often allow several explanations. A major 2023 assessment concluded that evidence is still insufficient to generalize that common fungal networks are widespread, stable support systems through which mature forest trees routinely improve seedling performance. And it found no published peer-reviewed evidence for the popular claim that old mother trees preferentially send resources and defense information to their own offspring. This does not mean fungal networks are imaginary. Roots can clearly share fungal partners, and substances can move through fungal hyphae. It means that a dramatic story told about the entire forest may be much more certain than the evidence beneath it. Natural soil is crowded with overlapping processes. Roots touch one another, release chemicals, compete for nutrients, alter microbial communities, and change moisture around them. Bacteria and non-mycorrhizal fungi occupy the same spaces. Water can carry dissolved compounds without using a fungal connection. Airborne chemicals released by damaged leaves can reach neighboring plants above ground. When a nearby plant changes its defenses, separating the contribution of the fungal network from every other pathway requires careful experimental controls. Researchers often place barriers between plants that block roots while allowing much thinner fungal hyphae to pass, then compare those systems with barriers that block both. Even this method has limits because barriers can change water flow, microbial movement, soil structure, and the amount of contact available to each organism. A clean-looking experiment may still simplify a relationship that is far more complicated in a real forest. Despite these challenges, controlled studies have produced evidence that fungal connections can influence defensive responses. In one experiment, tomato plants were linked through an arbuscular mycorrhizal fungus. When caterpillars attacked one plant, connected neighboring plants increased the activity of defensive enzymes, activated genes involved in the jasmonate defense pathway, and became more resistant to later insect feeding. Control arrangements designed to prevent the shared fungal connection did not produce the same response. The study showed that information associated with herbivore attack could pass through or depend upon the common network, although the precise traveling molecule was not conclusively identified. Saying that plants warned their neighbors may therefore be useful shorthand, but it adds intention that the experiment did not demonstrate. The attacked plant may release compounds into its roots as part of its own internal defense response. The fungus may detect those compounds, transport them, alter its own metabolism, or change what it delivers to another root. The neighboring plant may then sense that change and prepare its defenses. No participant needs to understand that another plant is in danger. Communication in biology can simply mean that a signal produced by one organism changes the behavior or physiology of another. Even then, scientists ask whether the signal evolved to inform the receiver or whether the receiver is merely exploiting information that was released for another reason. A plant that benefits competitors by deliberately warning them might lose a relative advantage. So theoretical work published in 2025 argued that truly cooperative, warning through plant fungus networks would evolve only under restricted conditions, and that neighboring plants may often be better understood as eavesdroppers, detecting changes that were not produced for their benefit. This distinction transforms the underground network from a friendly conversation into something more ecologically realistic. It can contain cooperation, competition, manipulation, surveillance, and accidental information all at once. A neighbor may benefit from detecting danger early, but the attacked plant may not gain anything from that benefit. The fungus may transport a compound because moving material serves its own physiology, not because it is acting as a messenger. In another situation, the fungus may influence both plants in a way that improves its access to carbon. The same pathway that carries useful information could also spread harmful substances. A fungal connection might transport defensive chemicals, allelopathic compounds that suppress neighboring plants, pathogens, or signals that make one host more vulnerable. Recent experiments have even shown that common mycorrhizal networks can facilitate the spread of plant disease-related signals or agents under particular controlled conditions, reminding researchers that connectivity is not automatically protective. The number of stars exceeds the grains of sand on Earth. One of astronomy's most famous claims may be true, false, or impossible to settle depending on a detail almost everyone leaves out. What exactly counts as all the sand on Earth? The statement is usually repeated as though scientists have counted every star and every grain, compared two finished totals, and declared the stars victorious. In reality, neither side can be counted directly. Both numbers are estimates built from samples, averages, and assumptions, and changing only one assumption can move the answer by hundreds or thousands of times. The scientifically safer version is that the observable universe may contain more stars than there are grains of sand on Earth's beaches, but even that comparison remains uncertain. Claiming that stars definitely outnumber every grain in beaches, deserts, riverbeds, and the seafloor goes beyond what has been reliably established. This uncertainty does not make the comparison meaningless. It makes it more educational, because it reveals how scientists estimate quantities far too large to count one by one. Begin with a beach. You would not kneel down and count every grain. You would measure or estimate the total volume of sand, take a smaller representative amount, determine approximately how many grains it contains, and multiply. The method sounds straightforward until you notice how strongly the result depends on grain size. A container filled with coarse grains holds far fewer pieces than the same container filled with fine grains. Make the average grain only half as wide, and many more grains can fit along the container's length, width, and depth. A small change in diameter can therefore produce a very large change in the final total. Beaches also differ in width and depth. Coastlines are irregular. Some shores are rocky rather than sandy, and sand continues beneath water where its boundaries become difficult to define. One recent back-of-the-envelope calculation used assumptions about global sandy coastline, average beach width and depth, and roughly millimeter-sized grains to estimate around 400 quintillion grains on the world's beaches. Under smaller grain assumptions, the total could increase enormously. That calculation also emphasized that adding deserts and ocean floor sediments would raise the number far beyond the beach-only estimate. Now consider the stars. Astronomers cannot point a telescope outward and count every star, because most are too faint, distant, or hidden within unresolved galaxies. They instead study galaxies whose brightness and stellar populations can be measured, estimate how many stars galaxies of different sizes contain, and extend those results across the observable universe. ESA describes a broad estimate ranging from roughly 10 sextillion to 1 septillion stars, a 1 followed by somewhere between 22 and 24 zeros, while NASA states that the total could reach 1 septillion. These are not precise census results. They are order of magnitude estimates reflecting uncertainty about faint galaxies, low-mass stars, and regions current telescopes cannot resolve individually. The Milky Way alone contains more than 100 billion stars. Yet even this nearby total is uncertain because humanity observes the galaxy from inside its disk, where dust blocks parts of the view and countless faint stars are difficult to detect. Low-mass red dwarfs complicate the count further. They shine weakly and are easily missed, but they are much more common than bright stars like the Sun. An image filled with brilliant stars therefore gives a distorted impression of the population. Most stars are not spectacular beacons visible across enormous distances. They are modest, cool objects contributing very little light individually, while contributing greatly to the total count. The same selection problem applies to galaxies. Large, bright galaxies are easy to find, while small, dim galaxies are not, even though the smaller ones may be far more numerous. A cosmic census must therefore estimate not only what telescopes detect, but what detection limits cause them to miss. This is why star estimates can differ by several orders of magnitude. One method may assume a very large number of galaxies and apply a typical stellar population. Another may account more conservatively for the fact that most Galaxies are far smaller than the Milky Way. A 2024 analysis in Scientific American used an estimated 2 trillion galaxies but assigned a much lower average stellar count because the majority would be small, producing about 20 quintillion stars, far below ESA's upper estimates. Using its separate estimate of beach sand, that calculation concluded that beach grains might outnumber stars by about 20 to 1. The article did not prove that sand had won. It showed that this familiar comparison is a Fermi problem, a rough estimate in which reasonable-looking assumptions can lead to dramatically different answers. If the higher astronomical estimate is closer to reality, stars could outnumber beach grains by thousands. If the lower stellar estimate and a high sand estimate are closer, sand could win. If the phrase includes all terrestrial sand rather than only beaches, the balance moves further towards sand because immense deposits lie in deserts, beneath oceans, along rivers, and inside geological layers. There is also no perfectly sharp boundary between sand, silt, gravel, crushed shell, volcanic fragments, and sediment cemented into rock. Should a grain buried kilometers underground count? Should sandstone count as sand if its grains have become joined together? Should particles resting on the ocean floor be included? And if so, to what depth? The title sounds precise, only because it hides every definition that would make the comparison possible. The word Earth is too large, and the word sand is too flexible. The star side contains a similar boundary problem. Astronomers can estimate stars in the observable universe, the region from which information has been available to us. But they do not know the number of stars in the entire universe. Space may continue far beyond the observable region, perhaps vastly farther than current measurements can reveal. If the whole universe is infinite and contains stars throughout, then the total number could also be infinite, and no finite quantity of terrestrial sand could compete. But science has not established that the universe is infinite, so adding unseen regions to the count would replace estimation with assumption. The honest comparison must therefore remain limited to the observable universe, even though the popular sentence often says simply, the universe. The problem becomes even more subtle when you ask what qualifies as a star. Does the count include stellar remnants such as white dwarfs and neutron stars, which no longer perform ordinary hydrogen fusion? What about brown dwarfs, objects that form somewhat like stars but never become massive enough for stable hydrogen fusion? Should a star that existed billions of years ago but has since died be included in a count of all stars that have ever existed, or only in the number existing now? Most popular estimates concern stars present within the observable universe during the cosmic periods represented by our observations, but light from distant regions reaches us from different ages. A perfect census of stars right now across the entire observable universe is not directly available because distant galaxies are not seen in a shared present. The simple comparison compresses a changing cosmic population into one imagined snapshot. Sand changes too. Waves grind rocks into new grains, rivers transport sediment, wind removes beaches, shells break apart, grains fuse into rock, and human industry moves enormous quantities. Neither total is a permanent number waiting to be uncovered. They are populations in motion, yet the comparison remains powerful because both possible answers are almost beyond intuitive understanding. Suppose the universe contains 10 sextillion stars. If you counted one every second without pausing, a human lifetime would barely begin the task. Even 1 billion seconds is more than 30 years, and a sextillion is a billion multiplied by a trillion. Human language can pronounce these values, but the mind cannot picture the individual objects they represent. You can visualize a handful of sand, perhaps a beach, or a sky scattered with stars. You cannot mentally display every grain along every shore or every star spread among billions or trillions of galaxies. Large numbers become words long before they become understanding. This is why the sand comparison was created. It takes something physically familiar, something that slips through your fingers, and places it beside a population too distant to experience directly. But the metaphor can accidentally become misinformation when awe replaces precision. The universe does not need an exaggerated fact to appear large. Even the most conservative stellar estimates describe more suns than a person could count across millions of human civilizations. Each star is not merely a point of light. It is an object with mass, temperature, chemical composition, internal structure, and a life history. Many may possess planets, moons, asteroids, and clouds of smaller material. Counting stars alone leaves out almost everything orbiting them and all the matter between them. Likewise, each grain of sand is not a featureless unit. Under magnification, grains reveal different minerals, colors, cracks, and histories. One may be a fragment of quartz carried from a mountain by a river. Another may come from coral, shell, volcanic glass, or older rock broken and reshaped over enormous spans of time. The comparison places two immense populations together, but each unit contains a story that the number erases. Science often needs this erasure. The moon is slowly drifting away from Earth each year. The moon is leaving Earth so slowly that you could never watch it happen. Yet every year, it moves about 3.8 centimeters farther away, roughly the width of a human thumb. This distance is measured with lunar laser ranging, a technique in which observatories send brief laser pulses toward reflective panels left on the moon by Apollo astronauts and Soviet robotic missions. A tiny fraction of the light returns to Earth, and the travel time reveals the moon's distance with extraordinary precision. The reason for the retreat begins in Earth's oceans. The moon's gravity pulls more strongly on the side of Earth facing it, and slightly less strongly on the far side, helping produce two tidal bulges. If Earth rotated at exactly the same rate that the moon orbited, those bulges would remain aligned with the moon. But Earth spins much faster, completing one rotation in about a day, while the moon requires roughly a month to orbit. Earth's rotation carries the tidal bulges slightly ahead of the moon's position. Their gravity then pulls the moon forward along its orbit. This extra pull transfers angular momentum from Earth's rotation to the moon's orbital motion. The moon gains orbital energy and shifts into a wider orbit, while Earth loses a tiny amount of rotational energy and turns slightly more slowly. Moving outward does not make the moon orbit faster. In a higher orbit, its average orbital speed becomes lower and the time required to circle Earth becomes longer. The moon's retreat and the gradual lengthening of Earth's day are therefore two parts of the same exchange. Ocean tides are especially important because moving water rubs against coastlines and the seafloor, converting some organized motion into heat. But the solid Earth also flexes under lunar gravity and contributes to the process. The exact recession rate has not remained constant throughout history. Continents move, oceans open and close, sea levels change, and the shapes of ocean basins determine how strongly tides resonate and dissipate energy. Today's rate cannot simply be multiplied backward to reconstruct the entire past. Geological records preserved in ancient tidal sediments, corals, and shells indicate that the moon was closer long ago, and that Earth's days were shorter. Hundreds of millions of years ago, a year contained more days because each day lasted less time. Soon after the moon formed more than 4 billion years ago, it was probably much closer still. Although the early tidal history remains difficult to reconstruct precisely, the moon may have originated after a massive collision between the young Earth and another planetary body, with debris eventually gathering into the satellite we know. Once established in orbit, tidal interaction began reshaping both worlds. It has already changed the moon more dramatically than many people realize. The moon is tidally locked to Earth, meaning it rotates once during each orbit and therefore keeps nearly the same hemisphere facing us. This was not necessarily its original state. Early tidal forces distorted the moon and dissipated its rotational energy until its spin became synchronized with its orbit. The so-called far side is not permanently dark. It receives sunlight just as the near side does, but it usually faces away from Earth. Earth is not yet locked to the moon because our planet still rotates much faster than the moon orbits, so the exchange continues. In a simplified system containing only Earth and the moon, The distant future could bring mutual tidal locking. Earth's day would become as long as the Moon's orbital period, and the Moon would remain over approximately the same region of Earth. However, this would require an immense span of time, and the Sun's evolution will transform the solar system before the idealized process can fully unfold. The current recession also changes how the Moon appears in the sky. As it moves farther away, its apparent size slowly decreases. Total solar eclipses are possible today because the Sun is about 400 times wider than the Moon, but also roughly 400 times farther away, allowing their apparent sizes to be remarkably similar. The match is not exact and varies because both Earth's orbit and the Moon's orbit are slightly elliptical. When the Moon appears large enough, it can completely cover the Sun and produce a total eclipse. When it appears smaller, a bright ring of sunlight remains, creating an annular eclipse. As the Moon continues to recede, total eclipses will eventually become impossible because even the nearest looking Moon will no longer appear wide enough to cover the Sun completely. This transition lies hundreds of millions of years in the future and cannot be dated with perfect precision because the Moon's recession rate will change, but it means humanity lives during a temporary astronomical era in which the apparent disks of the Sun and Moon can align with extraordinary precision. The Moon's departure is not a sign that it is about to escape Earth. It remains firmly gravitationally bound, and the widening of its orbit is extremely gradual. A few centimeters per year is tiny compared with an average Earth-Moon distance of about 384,400 kilometers. Even after 1,000,000 years at the present rate, which is not guaranteed to remain constant, the added distance would still be small compared with the orbit's total size. The retreat also does not noticeably weaken tides from one human generation to the next. Lunar tides will evolve over geological time, but present-day changes in coastlines, sea level, and climate can affect local tides far more strongly than the Moon's yearly recession. The measurement is valuable not because it predicts an immediate transformation, but because it allows scientists to test gravity and planetary motion with exceptional accuracy. Decades of laser-ranging data help refine the Moon's orbit, measure Earth's rotation and orientation, study movements in the lunar interior, and test whether gravity behaves as predicted by general relativity. The reflectors themselves require no electrical power. They are arrays of specially shaped mirrors that return incoming light toward its source, allowing experiments to continue long after the missions that placed them ended. The returning signal is extremely faint because the laser beam spreads during its journey, and most photons miss the reflector or fail to return to the telescope. Detecting even a few returning photons can provide a precise measurement when their timing is known. Through this patient experiment, a motion smaller than your yearly fingernail growth becomes visible across a distance greater than the circumference of Earth multiplied many times. The recession also reminds you that an orbit is not a perfectly frozen path. Earth and the Moon continually exchange energy and angular momentum, while the Sun and planets add smaller gravitational influences. The Moon's orbit changes in orientation and shape, and its distance varies throughout each month. The familiar circle shown in simple diagrams is only an approximation of a much richer motion. Even the length of Earth's day changes for several reasons besides lunar tides. Winds, ocean currents, earthquakes, melting ice, movements in Earth's core, and changes in the distribution of mass can slightly speed or slow the planet's rotation over shorter periods. Tidal friction produces a long-term slowing trend, but individual years can depart from it. Timekeeping systems occasionally account for differences between atomic clocks and Earth's irregular rotation, revealing that the planet itself is not a flawless clock. The Moon is partly responsible for this changing rhythm. Every tide raised along a coastline, every small flexing of the solid planet, and every fraction of rotational energy lost contributes to a transfer that has continued for billions of years. The effect is too gentle to feel, yet its cumulative history has helped transform Earth. A closer Moon in the distant past produced stronger tidal influences and a different rotational environment. As the Moon moved outward, Earth's days lengthened, changing the daily cycles experienced by oceans, atmospheres, and living organisms. It would be an exaggeration to claim that lunar recession alone directed the evolution of life, but the changing day length and tidal patterns formed part of the environment in which life developed. The moon also helps stabilize the tilt of Earth's rotational axis, limiting some of the extreme variations that might otherwise occur, although its stabilizing role is complex rather than absolute. The relationship is therefore not simply that a satellite travels around a planet. Earth and the moon have been reshaping one another since their earliest history. The moon raises tides on Earth. Earth's tidal response moves the moon outward, and the slowing planet changes the timing of both worlds. Neither body follows exactly the same rhythm it had in the past. This is why the moon's slow departure can feel strangely personal, even though it poses no threat. The moon appears permanent because it has watched over every human civilization, every migration, and every night remembered in recorded history. Across that entire span, however, it has never occupied precisely the same orbit. It was slightly closer when the first cities were built, slightly closer when the earliest cave paintings were made, and slightly closer when your own life began. The difference is far too small for your eyes to notice, but it is physically real. During an average human lifetime, the moon moves only a few meters farther away, less than the length of a small room. That small shift contains a much larger truth. Stability in nature often means change that occurs too slowly for one lifetime to witness. Identical twins have different fingerprints, despite identical DNA. Two people can begin life from the same fertilized egg, carry almost the same genetic instructions, and still leave completely different marks on every surface they touch. Identical twins form when one early embryo separates into two developing individuals, so they usually share nearly all of their DNA. Yet their fingerprints are not duplicates, because genes do not draw each ridge one by one like a fixed blueprint. DNA helps establish the general construction of the skin, the size and shape of the fingers, and the broad tendency to develop arches, loops, or whorls, but the final pattern emerges through a sensitive physical process inside the womb. Fingerprints begin forming during early fetal development, when the outer skin and deeper tissue layers grow at different rates. Temporary swellings called volar pads appear on the fingertips, palms, and soles. As these pads change shape and gradually flatten, the skin begins folding into raised friction ridges. Their broad arrangement is influenced by genetics, which is why identical twins may have fingerprints that look more similar than those of unrelated people. One twin may have a loop on the same finger where the other also has a loop, and the overall ridge flow may appear closely related. But similarity is not identity. The tiny details used to distinguish prints, where one ridge ends, where another divides, how ridges curve around a pore, and the spacing between neighboring lines are shaped by conditions too small and unstable for DNA to control precisely. Each fetus occupies a slightly different position. Each finger experiences its own pressure against the amniotic sac, the uterine wall, the umbilical cord, or another part of the body. The amount and direction of pressure change as the fetus moves. Blood flow, tissue growth, hormone exposure, nutrition, and the timing of development vary subtly from one location to another. Even neighboring fingers on the same hand do not experience exactly the same conditions, which is why your 10 fingerprints differ from one another, despite belonging to one genome and one body. Development at this scale contains what scientists sometimes call biological noise, tiny fluctuations in cell division, mechanical tension, and chemical signaling that can lead growing tissue down slightly different paths. These differences are not mistakes in the genetic program. They are part of how complex structures form. DNA sets rules and boundaries, while the physical environment helps determine the exact result. You can compare it to two rivers beginning on the same mountain. The landscape gives both rivers a general direction, but small differences in rock, soil, rainfall, and erosion make each channel unique. Fingerprint ridges develop through a similar interaction between inherited structure and local conditions. Once formed, the main pattern remains remarkably stable, because the ridges are anchored in deeper layers of the skin. Everyday cuts that affect only the surface heal while restoring the original arrangement. A deep injury that damages the underlying tissue may leave a permanent scar, but the scar becomes an added identifying feature rather than causing the print to transform into someone else's pattern. This stability is why fingerprints have been used for identification for more than a century. However, it is important not to turn their usefulness into an absolute claim that has been mathematically proven. No one has examined every fingerprint from every person who has ever lived, so science cannot demonstrate universal uniqueness through complete comparison. What can be said is that the combination of ridge patterns and microscopic details is extraordinarily distinctive, and identical twins provide strong evidence that matching DNA does not produce matching prints. Modern fingerprint analysis does not usually depend on the broad category alone. Millions of people may share loops or whorls. Examiners and automated systems compare many smaller features and their spatial relationships. The more corresponding details present in the same arrangement, the less likely an accidental match becomes. Still, fingerprint evidence is not infallible. A partial, blurred, stretched, dirty, or poorly collected print may contain too little information. Human examiners can make errors, and computer systems can return possible candidates rather than unquestionable answers. Responsible forensic practice therefore requires good quality evidence, careful comparison, documented procedures, and awareness of uncertainty. The biological distinctiveness of fingerprints does not guarantee that every real-world investigation will interpret them correctly. Identical twins also reveal why DNA identification and fingerprint identification answer different questions. A standard DNA profile may be unable to distinguish identical twins because the genetic markers commonly examined are the same. More advanced whole genome methods can sometimes find mutations that appeared after the embryo split, because twins do not remain genetically perfect copies throughout life. Cells continue dividing, and occasional mutations arise independently in each twin. Environmental exposures and aging also create differences between their bodies. Their DNA is therefore better described as nearly identical, rather than absolutely identical. Fingerprints, however, diverge before birth through developmental conditions, so they can usually distinguish the twins immediately. Facial recognition may struggle because twins share many inherited features, while fingerprints preserve the history of how each individual body grew in its own exact circumstances. This distinction reaches beyond forensic science. It demonstrates that genes are not complete scripts containing every final detail of a person. They provide instructions for building proteins, regulating development, and responding to the environment. But the finished organism emerges through interactions among genes, cells, physical forces, chance events, and experience. Identical twins may differ in height, disease risk, personality, immune responses, and even which conditions appear as they age. Some of those differences come from separate experiences after birth, while others begin much earlier. Twins can have different placental connections, unequal access to nutrients, different positions in the uterus, and small differences in developmental timing. Their fingerprints preserve a visible record of this early separation. Before either twin had a name, memory, or conscious experience, their bodies were already following slightly different physical histories. The ridge ending on one fingertip and the fork on another are not meaningful messages intentionally written into the skin, but they are traces of growth that can never be repeated in exactly the same way. This is why cloning would not create matching fingerprints either. A genetic clone would share the nuclear DNA of its donor, but it would develop in a different womb, at a different time, under different mechanical and biological conditions. Its fingerprints would be its own. Even if scientists could recreate an embryo with the same genome, they could not reproduce every microscopic pressure, cellular fluctuation, and movement that shaped the original hands. Identity is therefore not stored in DNA alone. The genome is powerful, but it is only one layer of the process. Your body is also a record of where development met circumstance. Fingerprints make that truth easy to see because they are both permanent and visible. The pattern on your finger was shaped before birth, survived childhood growth by expanding with the skin, and remains with you as your body changes. It does not reveal your personality, intelligence, future, or moral character. Despite old traditions that tried to read destiny from hands, its scientific value lies in distinction, not prophecy. It identifies the ridge arrangement, not the person's inner life. Yet there is something quietly profound in the fact that identical twins, who begin from one biological origin, still become physically distinguishable before they enter the world. Their differences do not wait for separate homes, friendships, choices, or memories. Development itself creates individuality. A shared genome can produce similar faces and related bodies, but it cannot force every cell to experience the same pressure or every ridge to follow the same path. Each twin arrives carrying evidence that sameness, at the level of instructions, does not produce sameness in the completed person. When you press your fingertip against glass, you leave behind more than oil arranged in curved lines. You leave a pattern created by inheritance, growth, motion, and microscopic chance working together months before your birth. No decision formed it, and no memory can recall its creation, yet it has accompanied every object you have held. Identical twins show the lesson most clearly. Two lives may begin with nearly the same genetic text, but biology does not print that text twice. It develops it, bends it through circumstance, and leaves each person with a signature that belongs not only to their DNA, but to the unrepeatable journey through which their body became their own. Your DNA contains enough information to fill a library. Inside nearly every cell of your body lies a molecular archive so compact that, if its chemical letters were printed as ordinary text, the sequence would occupy thousands of books. Yet calling it a library is only the beginning of what makes DNA extraordinary. A human genome contains roughly 3 billion pairs of chemical letters inherited as one set from each parent, giving most cells about 6 billion individual DNA letters in total. Written continuously in a simple typeface, one inherited set alone could fill several thousand average-sized books, depending on page size, spacing, and what is counted as a book. This does not mean your cells contain stories, sentences, or hidden paragraphs in the human sense. DNA is information because the order of its 4 chemical building blocks influences how cells construct and regulate proteins, copy themselves, respond to signals, and maintain a living body. The comparison with a library is therefore useful, but imperfect. A library is organized for a reader who can open one volume at a time, while a cell must constantly locate, copy, repair, silence, expose, fold, and interpret selected regions of DNA without tangling or destroying the rest. The entire genome is stored inside a nucleus, only a few millionths of a meter across. Even though the DNA from one human cell would stretch to roughly 2 meters if fully unwound. This is possible because DNA does not lie loose like thread in a box. It wraps around proteins called histones, forming repeating units that fold into chromatin and then into larger structures. The packaging is not merely a way to save space. It also helps control access. A tightly packed region may be difficult for cellular machinery to read, while a more open region can become active. The genome therefore resembles a library whose shelves can change shape, whose doors open only in certain rooms, and whose books may be readable in one cell but sealed in another. This explains how nearly every cell can contain essentially the same DNA while behaving so differently. A neuron, a liver cell, and a skin cell usually carry the same genome, yet they use different portions of it. The difference is not that each cell receives a separate manual. It is that each one follows a different program of gene activity. Chemical tags attached to DNA and histone proteins, along with regulatory molecules and the 3-dimensional folding of chromosomes, influence which genes become accessible. This layer of control is often called epigenetic regulation. It does not rewrite the basic DNA sequence every time a cell changes its behavior, but it changes how the sequence is used. A nerve cell keeps genes associated with electrical signaling active, while suppressing many programs needed in muscle or bone. A liver cell activates systems for metabolism and detoxification. The same archive supports many identities because its instructions are conditional, rather than arranged as one rigid sequence of commands. Even the word gene can be misleading if it makes you picture a clean sentence beginning at one point and ending at another. Human DNA contains roughly 20,000 protein-coding genes, far fewer than early researchers expected, and those genes occupy only a small fraction of the total genome. Much of the remaining DNA does not directly encode proteins. Some regions regulate when and where genes turn on. Some help organize chromosomes, maintain their ends, or support accurate division. Some produce functional RNA molecules that never become proteins. Other regions consist of repeated sequences, ancient viral remnants, mobile genetic elements, or stretches whose functions are still uncertain. Non-coding does not mean useless, but neither does it mean that every letter has a known purpose. The old phrase junk DNA encouraged the mistaken belief that everything outside genes was meaningless, while more recent exaggerations sometimes claim that nearly every part must perform a vital hidden function. The evidence supports a more careful view. Some non-coding regions are essential. Many influence regulation or chromosome structure, and others may have little effect under ordinary conditions. Evolution does not produce a perfectly edited manual. It preserves useful changes, tolerates neutral material, duplicates sections, rearranges old sequences, and leaves historical traces. Your genome is therefore less like a book written from beginning to end by one author, and more like an archive revised across billions of years, containing active instructions, regulatory notes, repeated passages, damaged fragments, borrowed elements, and older material repurposed for new roles. One of the most striking examples of this history comes from viruses. A noticeable portion of human DNA descends from ancient viruses that inserted genetic material into the cells of distant ancestors. Most of these sequences can no longer produce active viruses, but some were modified or recruited by evolution. Certain viral-derived genes became important in the development of the placenta, helping mammalian cells fuse in ways necessary for pregnancy. What was once an infection became, over evolutionary time, part of the biological machinery that allows new human life to develop. The genome is not isolated from the history of life. It is one of the places where that history remains physically recorded. Yet the information in DNA does not function alone. A genome placed inside a tube does not become a person. Development requires a living cell, nutrients, cellular structures, chemical gradients, physical forces, and signals exchanged among growing tissues. DNA does not contain a miniature image of your adult body or a complete frame-by-frame description of every event that will occur. It provides components and regulatory systems that interact with one another and with the environment. The shape of a hand, the wiring of the brain, the strength of bone, and the development of the immune system emerge through processes involving gene activity, cell communication, timing, feedback, and local conditions. This is why the genome should not be described as a complete blueprint in the ordinary architectural sense. A blueprint already specifies the final building in static detail. DNA is closer to a dynamic collection of recipes, switches, constraints, and self-modifying procedures executed by cells that are themselves products of earlier development. The instructions can produce different outcomes under different conditions, and many traits arise from the combined influence of thousands of genetic variants rather than one controlling gene. Height, metabolism, skin color, disease risk, and many aspects of brain development are shaped by networks of genes interacting with nutrition, hormones, experience, age, and environment. DNA influences possibilities and probabilities, but it does not write every future event in advance. Even two cells within the same body do not always retain perfectly identical sequences. Each time DNA is copied, repair systems correct most errors, but occasional changes remain. Sunlight can damage DNA in skin cells, chemicals can alter it, and ordinary cell division introduces mutations over time. Most mutations have no noticeable effect, some harm the cell, and a few contribute to cancer or other disease. Your body is therefore not composed of trillions of cells carrying one perfectly frozen edition of the genome. It is more like a vast collection of closely related copies, most nearly identical, some containing small printing changes acquired during life. The immune system takes controlled variation even further. Certain immune cells deliberately rearrange parts of their DNA to create an enormous variety of receptors capable of recognizing unfamiliar pathogens. This does not change the genome throughout the body, but it shows that DNA can be edited within specialized cells as part of normal biological function. A fixed archive becomes a generator of diversity. Information density is another reason DNA attracts comparison with advanced data storage. Because each position can contain one of 4 chemical bases, a DNA sequence can encode large amounts of information in a tiny volume. Researchers have demonstrated that digital files can be translated into artificial DNA sequences, synthesized, stored, and later read back. In principle, DNA can preserve enormous quantities of data for long periods if protected from heat, water, radiation, and chemical damage. This has inspired experimental storage systems in which images, documents, and other files are converted into base sequences. But natural DNA and engineered digital storage should not be confused. Your genome was not compressed by a programmer seeking maximum efficiency, and cells do not read it like a computer loading software from a drive. Biological meaning depends on location, folding, timing, chemical modification, and interaction with many molecules. The same short sequence can behave differently in different contexts. Parts of the genome overlap, and one region may influence several processes. Genes can also be edited after they are copied into RNA, allowing one DNA region to contribute to several related protein forms. The information is therefore layered and contextual, rather than simply stored as a linear message. When scientists sequenced the human genome, they did not instantly learn how a human being works. Reading the letters was a monumental achievement, but interpretation became the larger challenge. Researchers must determine which regions are active in particular cells, which variants alter disease risk, how distant regulatory elements contact genes through chromosome folding, and how combinations of changes influence development. Your skeleton is completely replaced every 10 years. The hardest tissue in your body is being quietly demolished while you sit still, then rebuilt in the same place by cells that never allow your skeleton to become as permanent as it appears. The familiar claim that your entire skeleton is replaced every 10 years points toward a real biological process, but it should not be interpreted as though every bone disappears on the same date and a new skeleton suddenly takes its place. Bone is renewed continuously and unevenly. On average, roughly 5 to 10% of the adult skeleton may be remodeled each year, so most of its material can be renewed over about a decade. But turnover differs greatly between bones, between regions of the same bone, and between individuals. Some tissue is replaced relatively quickly, while other portions may remain for decades. Your skeleton, therefore, has no universal expiration date. It is a living structure composed of regions of many different ages, all existing beside one another. This hidden renewal is called bone remodeling. It begins when large cells called osteoclasts attach themselves to a bone surface and create a sealed microscopic compartment. Inside that space, they release acid and enzymes that dissolve the mineral and organic material of old bone. They do not consume an entire bone like an animal stripping meat from a carcass. They excavate tiny pits and tunnels, removing material that may be old, damaged, poorly positioned, or no longer suited to the forces acting upon it. After the osteoclasts leave, other cells prepare the surface, and osteoblasts arrive to fill the cavity with fresh bone matrix. At first, this new material is soft and rich in collagen. Minerals are then deposited into it, gradually hardening the rebuilt region. Removing a small volume can take only a few weeks, while replacing and mineralizing it may require several months. Thousands or millions of these microscopic projects can be active at different locations without changing the recognizable outline of your skeleton. The bone remains your femur, rib, vertebra, or jaw, even while portions of its substance are being exchanged beneath the surface. The process is not random maintenance. Every step solves a biological problem. Walking, running, lifting, and even standing creates small stresses within bone. Most are harmless, but repeated loading can produce microscopic cracks. If bone were an inert material, such damage would slowly accumulate until failure became inevitable. Remodeling allows the body to identify vulnerable areas, remove damaged tissue, and replace it before small defects grow into fractures. Bone also adapts to use. Regions that regularly experience appropriate mechanical loading can become stronger or alter their internal architecture, while prolonged inactivity can encourage loss. Astronauts in microgravity, people confined to bed, and limbs kept immobile for long periods can lose bone because the skeleton no longer receives its usual mechanical signals. In contrast, weight-bearing activity can help maintain or improve bone strength, especially while the skeleton is developing. The bone is not consciously measuring exercise. Its cells sense deformation, fluid movement, chemical signals, and changes in force, then alter the balance between removal and formation. Remodeling turns physical experience into anatomy. A load repeated over months can influence where tissue is preserved, reinforced, or allowed to disappear. Much of this sensing is performed by osteocytes, former osteoblasts that have become enclosed within the material they helped create. They live in tiny spaces inside the bone and extend delicate branches through microscopic channels, forming a communication network throughout the tissue. When bone bends slightly under load, fluid shifts through these channels and affects the osteocytes. They can then release signals that influence osteoclasts and osteoblasts, helping decide whether a region should be maintained, removed, or reinforced. This means the solid-looking skeleton contains living cells buried within it, continuously gathering information about the conditions around them. A bone is not merely a mineral beam wrapped in flesh. It is a responsive organ supplied with blood vessels, nerves, marrow, collagen, minerals, and several specialized cell types engaged in constant communication. The outer shell, called cortical bone, is dense and provides much of the skeleton's stiffness and strength. Inside many bones lies trabecular bone, a lighter network of plates and struts arranged along lines of stress. Trabecular bone has far more exposed surface relative to its volume, so it generally remodels much faster than dense cortical bone. This is one reason the statement about a 10-year replacement cannot be applied equally everywhere. The delicate internal framework of a vertebra may change far more rapidly than deeply buried material in the shaft of a long bone. At any moment, your skeleton contains recently formed tissue, older tissue waiting its turn, and quiet regions not currently being remodeled at all. Bone renewal also serves a second function that has little to do with mechanical support. Your skeleton is the body's largest reservoir of calcium and phosphorus, minerals required not only for hard tissue but for nerve signaling, muscle contraction, blood clotting, energy use, and many cellular processes. The concentration of calcium in the blood must remain within a narrow range. If it falls, hormones can encourage the release of calcium from bone and increase its conservation or absorption elsewhere. If conditions change, mineral can be deposited again. This does not mean the body casually destroys healthy bones whenever you miss one calcium-rich meal. Regulation is more controlled and involves the intestines, kidneys, vitamin D, parathyroid hormone, and other signals. But it does mean that the skeleton participates in metabolism every day. It is both architecture and mineral bank. The body sometimes faces a conflict between keeping blood chemistry stable now and preserving skeletal strength for later. If removal repeatedly exceeds replacement, the immediate chemical needs of the body may be satisfied while the skeleton gradually becomes more fragile. In a healthy young adult, resorption and formation are usually balanced closely enough to maintain overall bone mass. With aging, hormonal changes, illness, certain medications, inactivity, inadequate nutrition, or other conditions, the balance can shift. Osteoclasts may remove more than osteoblasts replace, or new tissue may be formed too slowly. The skeleton can then lose mass even though remodeling continues. Renewal does not automatically mean improvement. A city can rebuild constantly while still losing buildings faster than it replaces them. Bone behaves in the same way. This imbalance lies at the heart of osteoporosis, a condition in which bone strength falls and fractures become more likely. The danger is not simply that bones become hollow, their internal architecture changes. Trabecular struts can thin, disconnect, or disappear, while the dense outer shell can become more porous. The remaining tissue may still contain living cells and continue remodeling, but the overall structure is less capable of distributing force. Because this deterioration can proceed without pain, a fracture may be the first obvious sign. The idea that the skeleton renews itself every decade can therefore create false reassurance. Replacement is not the same as restoration to an original perfect state. New bone is formed within the biological circumstances of the present body. If hormones, nutrition, movement, blood supply, or cellular function have changed, the new tissue may not fully replace what was removed. Aging bones are not simply young bones made from older material. Their cellular environment, internal organization, repair capacity, and accumulated history have changed. The skeleton is renewed, but it is not reset. This also explains why an elderly person does not receive an entirely youthful skeleton merely by surviving another 10 years. Remodeling preserves continuity and repairs damage, yet the process itself changes with age. Osteoblast formation may decline, osteocytes may become less effective, inflammatory signals may increase, and hormonal protection may weaken. The average age of the tissue may remain much younger than the person, but the system producing and maintaining that tissue belongs to an aging organism. Growth adds another layer. During childhood and adolescence, bones do more than replace old material. They lengthen, widen, change shape, and accumulate mass through a process called modeling. In remodeling, removal and formation occur in a coordinated sequence at approximately the same location, preserving the bone's general shape. In modeling, formation and removal can occur independently on different surfaces, allowing the entire structure to expand or reshape. Long bones grow at specialized plates near their ends until those plates close after adolescence. At the same time, bone is added to outer surfaces and removed from selected inner surfaces, increasing strength without making the skeleton impossibly heavy. By early adulthood, most people reach their peak bone mass, the largest reserve of bone they will carry. Genetics contribute strongly, but nutrition, hormones, movement, illness, and lifestyle during development also matter. Remodeling then becomes the dominant long-term maintenance process, although modeling can still occur when bones adapt to altered forces or weakening. This means the skeleton of childhood is not simply exchanged for adult material inside an unchanged frame. Its proportions and architecture are actively constructed as the body grows. Your immune system kills millions of cells every single second. Before you finish listening to this sentence, tens of millions of cells inside your body will have reached the end of their lives. Yet most of them will disappear so quietly that you will never feel a single one go. Researchers estimate that the adult human body turns over roughly 330 billion cells each day, which averages close to 4 million cells every second, although the rate varies with body size, health, age, and tissue activity. Most of this enormous numerical turnover comes from short-lived blood cells and cells lining the digestive system. The popular claim that your immune system kills millions of cells every second is therefore close to the correct scale, but misleading about the mechanism. Your body loses and replaces millions of cells each second, but the immune system does not actively hunt down and execute all of them. Many complete their natural lifespan, detect internal damage, or receive developmental signals that activate a controlled self-destruction program called apoptosis. Immune cells often arrive afterward to remove the remains. In other situations, however, specialized immune cells do deliberately kill cells that have become infected, dangerously abnormal, or potentially cancerous. The reality is not one endless massacre, but a coordinated system of retirement, inspection, targeted elimination, cleanup, recycling, and replacement. Without it, Your tissues would become overcrowded with aging cells. Infected cells could become factories for pathogens. Damaged cells might grow uncontrollably, and cellular debris would provoke inflammation throughout the body. Apoptosis is designed to prevent this chaos. A cell entering apoptosis does not usually swell and explode. It shrinks, disconnects from its neighbors, condenses its internal material, and divides itself into small membrane-wrapped fragments. This packaging keeps potentially harmful enzymes and molecules contained. The dying cell also changes the chemistry of its surface, displaying signals that act like a biological request for removal. One of the most important is a lipid called phosphatidylserine, normally kept on the inner side of the cell membrane, but exposed on the outside during apoptosis. Nearby phagocytic cells recognize this and other eat-me signals, surround the dying material, draw it inside, and digest it. The removal process is called efferocytosis, a word derived from the idea of carrying the dead to the grave. Macrophages are among its most important participants. They live throughout your tissues, continually sampling their surroundings and clearing cells that have completed apoptosis. Some dying cells are also removed by neighboring tissue cells rather than by professional immune cells, especially in places where rapid local cleanup is required. The efficiency is astonishing. Hundreds of billions of cells can die in a healthy body each day, yet microscopic examination rarely reveals large piles of corpses because removal normally occurs soon after death begins. The cleaner often reaches the cell before its outer membrane has broken, allowing the remains to be dismantled without an alarm. This is essential because the contents of a living cell are safe only while they remain inside it. If dying cells are left uncleared, their membranes eventually fail, and molecules normally hidden from the immune system leak into surrounding tissue. Those molecules can be mistaken for danger signals, attracting more immune cells and creating inflammation. Material from the cell's nucleus can also become visible to the immune system, raising the risk that immune defenses will begin reacting against the body's own components. Defective clearance of apoptotic cells has therefore been associated with chronic inflammatory and autoimmune conditions, including systemic lupus erythematosus, while failed cleanup inside artery plaques can contribute to unstable regions filled with dead material. A peaceful cell death is only peaceful if someone removes the body. The macrophage does more than swallow waste. After engulfing an apoptotic cell, it often shifts towards signals that suppress unnecessary inflammation and encourage repair. It can release molecules that tell surrounding immune cells that the danger is passing, support tissue rebuilding, and prepare itself to consume additional corpses. A single macrophage may clear several dying cells in succession, processing their proteins, fats, sugars, and nucleic acids as biological material that can be broken down or reused. Efferocytosis is therefore closer to controlled recycling than simple disposal. The molecules that once formed one cell can eventually return to circulation or become raw material for other processes. Your body remains materially continuous, partly because it repeatedly dismantles itself and reuses what can be saved. Yet not every dying cell chooses its own exit. Cytotoxic T lymphocytes and natural killer cells are immune cells specialized for direct cellular killing. A virus survives only by entering a host cell and using its machinery to produce more viruses. Antibodies may neutralize viruses outside cells, but once infection is hidden inside, destroying the infected cell can become the most effective way to stop production. Cytotoxic T cells inspect molecular fragments displayed on cell surfaces. Almost every nucleated cell continually presents small samples of the proteins being made inside it. If a T cell recognizes a fragment associated with a virus or a dangerous abnormality, and the surrounding signals support attack, it can form close contact with the target and release specialized granules. These contain perforin and granzymes. Perforin helps granzymes enter the target, and the granzymes activate internal pathways that drive the cell toward programmed death. Natural killer cells can use a similar system, but their recognition strategy differs. They evaluate a balance of activating and inhibitory signals, Healthy cells usually display molecular signs that tell natural killer cells to leave them alone. Infected, stressed, or transformed cells may lose these protective signals or display new danger signals, shifting the balance toward attack. Natural killer cells can therefore respond rapidly without needing the same kind of prior antigen-specific training required by cytotoxic T cells. This targeted killing is more precise than the image of an immune cell firing toxins randomly into tissue. The killer cell forms an organized junction with its target and directs the lethal molecules into the narrow space between them, limiting harm to nearby healthy cells. It can then detach and search for another target. The doomed cell activates much of its own death machinery, allowing it to be dismantled in an orderly form that can later be cleared. The immune system is not simply smashing infected cells open, because rupture could scatter viruses, inflammatory material, and damaged contents. It is often forcing dangerous cells to close themselves down. Cytotoxic T cells can also activate death receptors on the target's surface, triggering another route into apoptosis. These mechanisms make cellular killing a partnership between an external immune decision and an internal self-destruction program. The attacking lymphocyte identifies the threat, but the target's molecular machinery performs much of the dismantling. This process happens throughout infections, yet the number of cells killed varies enormously. During a mild infection, only a limited population may be targeted. During a severe viral disease, widespread cellular destruction can contribute to organ damage, sometimes because the pathogen injures cells directly, and sometimes because the immune response damages infected tissue while trying to stop it. An immune attack can save the organism while sacrificing part of the organ. This is one reason inflammation and cytotoxicity must be regulated rather than maximized. A stronger response is not always a better response. Too little killing allows infection to spread. Too much can destroy the tissue the immune system is meant to protect. The immune system must continually make decisions with incomplete information, distinguishing dangerous change from normal variation. Cancer makes that distinction especially difficult because a cancer cell is not an obvious foreign invader. It descends from the body's own cells and retains many normal features. Some cancer cells produce abnormal proteins or unusual amounts of ordinary proteins that immune cells can detect. Natural killer cells may recognize stress signals, while T cells may respond to fragments created by mutations. This process is often called immune surveillance, but it is not a perfect patrol that destroys every potential tumor before it forms. Many genetically damaged cells repair themselves or activate apoptosis without direct immune involvement. Others stop dividing permanently through a state called senescence. Some are removed by immune cells. A few acquire combinations of changes that allow continued growth while avoiding detection. Tumors can reduce the signals that make them visible, produce chemicals that suppress nearby immune cells, recruit cells that protect them, or activate checkpoint molecules that function like brakes on T-cell activity. Modern cancer immunotherapies work partly by releasing these brakes or by engineering immune cells to recognize particular targets. But even these treatments help only some cancers and can cause severe side effects when immune activation becomes difficult to control. The existence of cancer does not prove that immune surveillance is useless. It reveals that biological inspection is an evolutionary contest in which abnormal cells can sometimes learn to hide. The immune system itself also depends on massive cell death.